a faint red smear appears on a screen, so small that it barely seems worth fearing. It is not a monster, it is not a signal calling our name, it is not a ship, or a weapon, or proof that something is watching us from the dark. It is only light, stretched thin by the expansion of the universe, arriving after a journey so long that almost everything familiar to us had not yet happened when it began. But that is exactly why it unsettles people who study the sky. Because when that ancient light is split apart, measured, checked, and placed on the timeline of cosmic history, it seems to come from an age when the universe should still have been raw, young, unfinished. Mostly hydrogen and helium, with only the first generations of stars beginning to teach darkness how to shine. And yet, out there, near the edge of observable time, astronomers keep finding signs of structure. Galaxies that look brighter than expected, systems that may have gathered mass quickly, chemical clues that suggest stars had already lived and died fast enough to seed space with heavier elements. Not proof that our understanding is broken, but pressure against the comfortable version of the story. Welcome to the channel. If you enjoy calm, evidence-grounded journeys through the strange edges of space, subscribe and stay with us. And before we go deeper, leave a comment with the discovery that feels most unsettling to you. Galaxies forming too early, thousands of distant planets, or the silence from worlds where life might exist. Because that silence is not where the discomfort begins. It begins with light. For most of human history, deep space was not a place we could interrogate. It was a black ceiling with sparks in it. Then telescopes became larger, detectors became colder, mirrors became cleaner, and slowly the ceiling turned into a time machine. Every farther galaxy became a younger galaxy. Every redder glow became a message from a more primitive universe. The deeper we looked, the more we expected to see things becoming simpler. Fewer heavy elements, fewer mature systems, fewer settled shapes. That expectation made sense. The early universe had rules. After the Big Bang, it expanded and cooled. The first atoms formed. Gravity began pulling matter into denser regions. Stars ignited. Inside those stars, simple elements were fused into heavier ones. Some stars died violently, spreading carbon, oxygen, silicon, iron, and other ingredients into space. Later stars and planets inherited that enriched material. So when astronomers look extremely far away, they are not only looking across distance, they are looking backward, toward a time before that long chemical chain should have had much room to operate. This is why some of the newest deep space observations feel so strange. A galaxy from the first few 100 million years of cosmic history is not just far away. It is a test of how quickly the universe could organize itself. It asks how fast gas could fall together, how fast stars could form, how fast those stars could pollute their surroundings, and how fast enough light could be produced for our instruments to see it. The James Webb Space Telescope was built for exactly this kind of question. Its gold-coated mirror gathers infrared light, the kind of light that very distant galaxies become after cosmic expansion stretches their original ultraviolet and visible glow. JWST does not simply take pretty pictures. It measures ancient photons that have been pulled like warm glass across billions of years. And when those photons reach us, they are faint. They have crossed expanding space. They have passed through clouds of gas, through eras of galaxy growth, through a universe that changed while they travelled. By the time they land on a detector near Earth, they are almost nothing. Yet almost nothing is enough. From that weak signal, scientists can estimate redshift. Redshift tells them how much the universe has expanded since the light began travelling. A high redshift means the galaxy is not merely distant, it belongs to a younger cosmic era. Some confirmed and candidate galaxies found with JWST sit so far back that they force astronomers to ask whether early star formation was more efficient than expected, or whether assumptions about dust, mass, and light need adjustment. That last phrase matters. Adjusted, not abandoned. This is where popular headlines often go too far. A strange early galaxy does not mean the Big Bang is false. It does not mean physics has collapsed. It does not mean scientists were lying, or that space agencies are hiding a cosmic secret. Real science is more interesting than that. The tension is not between truth and conspiracy. It is between a model that worked well broadly and evidence sharp enough to expose where details are incomplete. A map can be accurate and still become embarrassing when the road turns out to have more branches than expected. The early universe is one of those roads. Before JWST, astronomers already knew that galaxies formed early. Hubble had shown distant smudges, deep fields, young systems scattered across ancient light. But JWST changed the texture of the problem. It could see infrared wavelengths with extraordinary sensitivity. It could separate light into spectra. It could turn a faint candidate into a physical question. How old is it? How bright is it? How massive might it be? What elements leave fingerprints in its glow? And once you start asking those questions, the universe stops feeling like a clean timeline. Imagine expecting to open the first pages of a book and find rough sketches, only to discover paragraphs, punctuation, and names already written in the margins. You would not throw the book away. You would ask how the writing appeared so quickly. That is the mood around some of these discoveries. Not panic, not terror. A quieter kind of worry. The worry of seeing maturity where youth was expected. The worry of realizing that the universe may have been more efficient at building luminous structures than our best simplified stories allowed. The worry of knowing that every better telescope does not just answer questions, it manufactures sharper ones. And the chemical part of the story makes the unease deeper. Hydrogen and helium are easy for the early universe. They come from the first minutes of cosmic history. Oxygen does not. Carbon does not. Iron does not. Those elements require stars. They require pressure, heat, fusion, collapse, death, and dispersal. So when astronomers detect or infer heavier elements at very early times, they are reading not one event, but a compressed history. Stars must have formed, evolved, exploded, or shed material, and enriched the gas fast enough for those signatures to appear. That does not make the observation impossible. Massive stars can live short lives. Starbursts can be intense. Gravity can be brutal in dense early regions. But it does make the early universe feel less sleepy, less gradual, less like a slow dawn, and more like a machine that found its rhythm almost immediately. This is the first layer of why scientists are paying such close attention to what we are finding in deep space. Deep space is not only showing us distance, it is showing us speed. The speed of structure, the speed of chemistry, the speed at which darkness became crowded with objects bright enough to leave a mark on instruments built by a species that would not exist for more than 13 billion years. And once that idea settles in, the next discovery becomes harder to dismiss as isolated. Because the universe is not only building galaxies earlier than expected, it is also building worlds almost everywhere we learn how to look. Because once planets enter the story, deep space stops being only about the beginning of time. It becomes about possibility, not the dramatic kind of possibility that proves life is waiting around every star. Not the easy version, where every blue dot becomes another Earth, and every distant atmosphere becomes a promise. The real version is harder. More planets mean more chances, but also more unknowns. More worlds mean more chemistry, more failed experiments, more hostile surfaces, more atmospheres stripped away by radiation, more oceans that may never form. More systems where the right ingredients appear, but never arrange themselves into anything alive. For a long time, the planets we knew were the ones that circled our own sun. Mercury, Venus, Earth, Mars, the giant outer worlds, the icy moons, the broken leftovers in the asteroid belt and Kuiper belt. That was our sample. One star, one system, one arrangement. It was easy, without meaning to treat it as normal. Then the exoplanet era broke that illusion. The first confirmed planets around other stars did not arrive as gentle copies of Earth. Many were strange from the beginning. Giant planets orbiting close to their stars, worlds moving around dead stellar remnants, systems packed tighter than ours, planets where years last only days, bodies so hot that rock may vaporize, others so cold that familiar chemistry slows almost to stillness. The message was not that the universe had made Earth again and again. The message was that planet formation was far more inventive than our one example had prepared us to imagine. That is part of what makes the deep space discoveries uncomfortable. We wanted planets to answer the old question simply: are there other worlds like ours? Instead, planets complicated the question. They showed us that nature can make many kinds of worlds, and only some may resemble anything we would recognize as habitable. A planet can sit near the right distance from a star and still be dead. It can have the right size and the wrong atmosphere. It can have water once and lose it. It can have carbon, nitrogen, oxygen, and still never cross the invisible threshold between chemistry and biology. It can orbit a star that flares too violently, or rotate in a way that leaves one side burned and the other frozen. It can look promising from far away and become less promising with every better measurement. This is why the number of known exoplanets matters, but not in the simple way headlines often suggest. Thousands of confirmed worlds do not prove the galaxy is full of life. They prove that planets are common enough for the question of life to become sharper. When there were no known planets around other stars, the silence could hide behind ignorance. Maybe worlds were rare. Maybe the solar system was unusual. Maybe there simply were not enough places for life to begin. That shelter is shrinking. Every confirmed planet removes a little more of the excuse. Every rocky candidate, every atmosphere study, every system with multiple worlds adds weight to the same quiet problem. If planets are common, and if chemistry is common, and if stars have been forming for billions of years before the sun was born, then where does life fit into the pattern? That question does not have to be answered with aliens. In fact, the safest and most honest answer is that we do not know. But not knowing becomes more meaningful when the search becomes more capable. Telescopes can now do something that would have sounded almost magical to earlier generations. They can examine some atmospheres of planets around other stars. They do this not by visiting the planets, and not by seeing continents or oceans, but by watching starlight change. When a planet crosses in front of its star from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere, if it has one. Different molecules absorb different colors. In that dim signature, scientists search for gases, clouds, haze, heat, chemistry, and sometimes possible signs that something unusual may be happening. But even here, the universe refuses to be simple. A molecule can have more than one source. Methane can be biological in some contexts and geological in others. Oxygen can be produced by life, but there are also non-biological pathways under certain conditions. Carbon dioxide can reveal an atmosphere's structure without revealing life. Water vapor can be exciting and still not enough. A possible biosignature is not a discovery of biology, it is a demand for caution. That caution is where the tension lives. Because the public wants a yes or no answer, scientists often have to live inside a probability cloud. Maybe this atmosphere contains a clue. Maybe the data are noisy. Maybe the star is contaminating the signal. Maybe clouds are hiding the lower atmosphere. Maybe the planet is not the kind of world we imagined. Maybe the same chemistry that makes the planet interesting also makes it misleading. The deeper we look, the more the universe gives us half-open doors. And then, beyond the planets themselves, there is the silence. Not poetic silence, measured silence. The kind that comes from pointing a giant radio telescope toward a system that looks scientifically interesting. Sweeping through frequencies, removing interference, checking candidate signals, comparing patterns, and ending with no credible technosignature. That result can sound boring. No signal, no contact, no discovery. But in science, a careful non-detection is not nothing. It narrows the room. When astronomers search a system like TRAPPIST-1, they are not searching every possible form of intelligence. They are not listening for every technology, every message, every civilization, every beam, every machine, every unknown communication method. They are searching within specific frequencies, sensitivities, times, assumptions, and signal types. A non-detection does not tell us nobody is there. It tells us that, under those conditions, no signal of that kind was found. That distinction may seem small, but it is the difference between honest science and myth. The silence becomes unsettling, not because it proves loneliness, but because it becomes cleaner. Better instruments make better absences. They turn the unknown into a shaped negative space. We can say, not this kind of transmitter at this strength during this observing window, not this simple version of the story, not the easiest answer. And so the silence begins to feel less like emptiness and more like a boundary. That boundary matters because TRAPPIST-1 is not just any star in the public imagination. It is a nearby ultra-cool dwarf star with a compact system of rocky planets, several of which have often been discussed in relation to habitability. It is not a copy of the solar system. Its planets orbit close to a small, dim star. They may face tidal locking, stellar activity, atmospheric loss, or other challenges. But because the system is nearby and rich with rocky worlds, it became one of those places where the old question naturally gathers. If life can emerge elsewhere, could systems like this matter? Then the telescope listens, and nothing clear comes back. Again, that does not mean no life. It does not even mean no technology. It means the universe has refused the simplest dramatic payoff. It has given us a target full of possibility, instruments capable of serious searching, and then a result that deepens the question rather than resolves it. This is one of the most difficult emotional shifts in modern astronomy. The more we discover, the less satisfying our old guesses become. Before exoplanets, people could imagine the universe however they wanted. Rare Earth, crowded galaxy, empty stars, living worlds everywhere, dead rocks everywhere. There was so little evidence that almost any story could survive. But now the evidence is arriving, and it is not arranging itself into a clean answer. Worlds are common. Earth-like certainty is not. Chemistry is everywhere. Biology is still unconfirmed. Searches are improving. The silence remains. That combination is more unsettling than a simple discovery would be. A simple discovery would give the mind something to hold. A confirmed signal. A clear biosignature. A second living world. But instead, the universe gives us abundance without confirmation. It gives us scale without resolution. It fills the galaxy with planets, then asks us not to mistake quantity for companionship. And somewhere in that gap, the idea of deep space changes again. It is no longer just the ancient light of galaxies. It is no longer only the cosmic dawn, where stars first learned to manufacture oxygen and carbon. It is also a living catalogue of failed and possible homes, systems that formed differently, atmospheres that evolved under different suns, worlds that may have oceans beneath ice, or lava under skies of vapour, or clouds filled with chemistry we barely know how to interpret from a few pixels of light. The discomfort comes from realising that the universe is not hiding because it is empty. It may be hiding because it is too varied. A signal can be missed because it is weak. A biosignature can be confused because chemistry imitates life. A habitable zone can be misleading because habitability is not only distance from a star. A planet can be counted, named, measured, and still remain almost completely unknown. This is what makes the next frontier so important. Scientists are not only collecting objects now, they are collecting contexts. The mass of a planet, the radius, the density, the type of star, the orbit, the atmosphere, the radiation environment, the age of the system, the presence or absence of neighbouring worlds. Each detail changes the meaning of the others. A small rocky planet around a calm star does not tell the same story as a small rocky planet around a flaring red dwarf. A gas-rich atmosphere on a warm planet does not mean the same thing as a thin atmosphere on a cooler one. A molecule seen once with uncertain data does not carry the same weight as multiple molecules measured repeatedly with different instruments. Deep space is becoming less like a gallery of distant objects and more like a courtroom of incomplete evidence. And the evidence does not all point in one direction. That is what scientists are starting to worry about. Not in fear, but in discipline. The universe is becoming observable enough to remove easy answers, but not yet observable enough to replace them with final ones. It is the uncomfortable middle stage of discovery, where mystery stops being vague and starts becoming measurable. For viewers, this can feel frustrating. We want the dramatic sentence: life found, aliens detected, Big Bang disproved, Earth not alone, Earth alone, danger incoming, mystery solved. But the real sentence is quieter and more powerful. We now know enough to know that the universe is not simple. That may be the most honest beginning of all. And once the universe stops being simple, the word finding begins to mean something different. It no longer means one shocking object in the dark. It means a pattern emerging across instruments that were never designed to flatter our assumptions. A space telescope sees galaxies too far back in time to feel comfortable. Planet hunting surveys reveal worlds in arrangements that our solar system never taught us to expect. Radio telescopes listen to promising stars and return with disciplined silence. Spectrographs pull chemical fingerprints out of light so faint that the signal has to be protected from noise, dust, the telescope itself, and even the star behind the planet. None of these discoveries alone is enough to rewrite everything. Together, they change the emotional weather, because science is not only built from answers, it is built from pressure. A model can survive a strange galaxy, then another, then a population that looks brighter than expected. A habitability idea can survive one harsh planet, then another, then 1,000 worlds that refuse to become Earth with different skies. A search for intelligence can survive silence, but as the searches become more precise, the silence becomes less vague. The room grows smaller. The shadows become shaped. This is where deep space becomes uncomfortable in a way that is easy to misunderstand. The discomfort is not supernatural. It is statistical. It is chemical. It is observational. It comes from the slow collapse of excuses. For example, when astronomers study early galaxies, they are not merely asking whether a distant object exists. They are asking how much gas it contains, how rapidly that gas could fall into stars, how much dust may be hiding or reddening the light, whether the galaxy's brightness is being boosted by a rare alignment, and whether the inferred mass is as large as it first appears. They compare spectra, models, simulations, uncertainties, and selection effects. Every correction matters. A galaxy can look too massive and later become less massive with better analysis. A candidate can look record-breaking and later move into a more ordinary category. A strange result can be partly explained by dust, starbursts, or measurement limits. This is normal. It is how the universe is slowly separated from our first impression of it. But after all the corrections, the pressure does not always disappear. That is why the early universe remains so compelling. It is not the cheap drama of impossible galaxies. It is the more durable question of how quickly cosmic structure could accelerate from smooth beginnings into luminous complexity. The first stars may have been massive. They may have lived brief, violent lives. Dense regions may have formed stars with surprising efficiency. Feedback from radiation, supernovae, and black holes may have shaped the early gas in ways that simulations are still trying to capture. So the worry becomes precise. Not how can this exist, but which part of our formation story is too slow, too clean, or too incomplete? That is a much better question. It also points toward a deeper truth. The universe does not have to violate physics to humble us. It only has to use physics in combinations we did not expect. A galaxy that formed early is not magic. It is gravity, gas cooling, dark matter structure, radiation, star formation, feedback, and time. But if all of that happened faster or more intensely than expected, then our mental picture of the cosmic dawn has to change. The dawn becomes less like a gradual light spreading over a quiet horizon, and more like fires igniting in pockets of darkness. some of them already bright enough to be seen from the far future. That image matters because it sets up the rest of the episode. The universe is not strange because it is lawless. It is strange because lawful things, given enough scale, produce outcomes that feel almost personal in their challenge. This is also true with planets. Planet formation begins in disks of gas and dust around young stars. Tiny grains collide, stick, break, settle, and collide again. Over time, some grow into pebbles, then planetesimals, then embryos, then worlds. Gravity sculpts the disk, radiation strips it. Giant planets migrate. Smaller planets are scattered, swallowed, or locked into resonances. Moons form, atmospheres are captured or lost. Impacts erase and create. A planetary system is less like a diagram and more like weather frozen into architecture. Our own solar system is one result of that process, but not the master template. Hot Jupiters showed that giant planets can end up extremely close to their stars. Super-Earths and mini-Neptunes showed that common planet types may exist that our solar system does not even contain. Compact systems showed that multiple rocky worlds can orbit closer to their star than Mercury orbits the Sun. Circumbinary planets showed that some worlds move under two suns. Rogue planet candidates suggested that some bodies may wander without a host star at all. Every category took something that once felt stable and loosened it. The unsettling part is not just variety, it is implication. If planetary systems are so diverse, then habitability may be more fragile, more local, and more conditional than a simple right distance from the star can capture. Water matters, but so do atmosphere, magnetic environment, geologic cycling, stellar radiation, impact history, orbital stability, planetary mass, and time. Life, at least life as we understand it, may require a chain of conditions, each one vulnerable to breaking. That makes the abundance of planets feel double-edged. The galaxy may be full of worlds, but that does not mean the galaxy is full of homes. And if a planet is not a home, it can still teach us something. A scorched planet can teach us atmospheric loss. A swollen planet can teach us stellar heating. A dense rocky world can teach us composition. A planet in a resonant chain can teach us orbital history. Even a dead world adds data to the larger question of how nature builds and ruins possibility. This is why scientists are careful with excitement. They have seen how easily imagination outruns measurement. A planet is announced, and the public wants oceans. A molecule is hinted, and the public wants biology. A nearby star has rocky planets, and the public wants neighbours. But instruments do not deliver neighbours. They deliver signals. A dip in starlight, a tiny wobble, a spectrum with uncertain features, a transit repeated enough times to trust, a statistical population that reveals what single planets cannot. Science must move from signal to explanation, one cautious step at a time, because the universe has many ways to imitate the thing we hope to find. That is especially true for life. Life is not just chemistry. It is chemistry with memory, reproduction, adaptation, energy flow, and history. From far away, we cannot see cells. We cannot watch evolution. We cannot scoop an ocean from an exoplanet and test it in a laboratory. We can only search for environmental clues that might be hard to maintain without biology, while also asking whether geology, sunlight, atmosphere, or planetary history could produce them without life. That is why a biosignature debate is not a failure. It is exactly what the field should look like before certainty exists. A possible clue appears. Scientists test alternate explanations. Some argue it may be interesting. Others argue the data are not strong enough. More observations are proposed. The claim narrows or strengthens. The public, impatient for revelation, may hear contradiction, but the method is working. This is what honest contact with the unknown sounds like before the unknown becomes known. And yet, even when handled carefully, these debates change us. They make it impossible to look at the night sky as empty decoration. Somewhere around those stars are planets, with atmospheres in motion. Somewhere, rocks are melting. Oceans may be freezing. Clouds are forming. Ultraviolet radiation is tearing molecules apart. And chemistry is trying combinations that no human laboratory has ever fully imagined. Most of it may be lifeless. Some of it may be briefly habitable. A tiny fraction may cross into biology. We do not know which fraction. That number may be the most important unknown in the galaxy. If life is easy, then silence becomes strange. If life is rare, then Earth becomes more precious. If simple life is common, but intelligence is rare, then the universe may be biologically rich and technologically quiet. If intelligence is common but short-lived, then deep space may be filled with ruins, missed signals, and civilizations separated by time rather than distance. If advanced life avoids broadcasting or uses methods we do not recognize, then our searches may be like listening for drums in a world that communicates with light. Every possibility is unsettling in a different way. This is the true power of deep space discovery. It does not give us one fear, it gives us a branching tree of questions, and each branch leads away from human certainty. The early galaxies ask whether cosmic structure grew faster than expected. The exoplanets ask whether worlds are common but homes are rare. The atmospheres ask whether chemistry can imitate biology. The radio searches ask whether silence means absence, distance, timing, wrong assumptions, or simply not enough sensitivity yet. And then, as if images and signals were not enough, deep space sends material through our own neighborhood. An interstellar object is different from a distant galaxy or an exoplanet. It is not just light from far away. It is a body that formed around another star, escaped its original system, crossed the dark between stars, and entered ours. For a brief time, something shaped by another planetary environment becomes observable from inside the solar system. That is not evidence of intelligence. It does not need to be. A natural object from another star is already extraordinary. Its ices, dust, gases, rotation, trajectory, and chemistry become a sample of processes we usually have to infer from light. When such an object passes near enough to study, it turns interstellar space from an abstraction into a delivery route. The galaxy is not only out there, sometimes pieces of it arrive. And that changes the tone again, because if other systems can send us debris, then the solar system is not sealed. It is moving through a galaxy with traffic too sparse to feel, but real enough to measure. Most visitors will pass unseen. Some may be too dark, too fast, or too far away when they cross our instrument's reach. The few we detect are probably only the brightest hints of a much larger population. In that sense, deep space is not silent at all. It is constantly exchanging matter, light, radiation, gravity, and information. We are only just becoming sensitive enough to notice. And when something arrives from another star, it carries a kind of evidence that no telescope image can fully replace. Light tells us what happened from far away. It can be stretched, absorbed, scattered, and filtered through dust. It can show us a galaxy as it was near the beginning of time, or a planet blocking a tiny portion of its star. But an interstellar object is matter. It has a path, a shape, a surface, a coma if it warms enough, a tail if sunlight releases gas and dust from its body. It has chemistry that was not assembled inside our solar system. That is why objects like this matter so much. They are not visitors in the science fiction sense. They are not messengers with intentions. They are leftovers, fragments, frozen records of distant construction sites. Somewhere, around another star, a planetary system formed with disks, collisions, gravity, migration, and loss. Some material was thrown away, maybe by giant planets, maybe by close stellar encounters, maybe by the violent shuffling of young worlds before their orbits settled. After that, the fragment drifted through interstellar space for an unknown span of time, cold and dark, until the geometry of the galaxy brought it through ours. To the public, the arrival can feel eerie because it crosses a boundary we usually imagine as sealed. We think of the solar system as a home with walls, the sun at the centre, planets in orbit, comets in distant reservoirs, and beyond that, the stars. But the real boundary is porous. Gravity reaches outward, radiation streams away, dust drifts through, cosmic rays arrive, interstellar gas flows past, and occasionally something large enough to track moves through the inner solar system on a path that does not belong to the sun. That path is the first clue. An ordinary comet from our solar system follows an orbit shaped by the sun. It may be long and stretched, but it remains bound. An interstellar object moves differently. Its speed and trajectory reveal that it is not simply returning from the far edge of our own system. It is passing through. The sun bends its path, warms it, exposes it, but does not own it. There is something quietly humbling about that. For billions of years, Earth has moved around a star that seemed central to every human story. Then one day, a faint moving point appears in survey data, and the orbit says, "This did not come from here." Not hostile, not miraculous, just not ours. That single phrase is enough to change the mood. The first confirmed interstellar object, 1I/Oumuamua, caused intense debate because it looked unusual, moved unusually, and gave astronomers only a short window to observe it. Its shape, brightness changes, and non-gravitational acceleration led to many hypotheses. Most scientific explanations stayed within natural possibilities: an unusual fragment, a nitrogen ice body, a hydrogen-rich object, a piece shaped by processes not common in our sample. But the uncertainty opened space for speculation. Then came 2I/Borisov, much more clearly comet-like, with gas and dust that scientists could study as it passed. It reminded researchers that interstellar visitors did not have to be mysterious because they were artificial. They could be mysterious because another natural planetary system had made them. That distinction is important. Nature is strange enough. By the time another confirmed interstellar comet entered the conversation, the scientific value was not in asking whether it was a spacecraft. That is the cheap question. The better question was what its chemistry could tell us about the system that produced it. If the gases released by sunlight show unusual ratios, if carbon dioxide dominates differently, if methanol, water, cyanide-bearing molecules, or dust behave in ways that differ from familiar solar system comets, then the object becomes a moving laboratory of another star's debris. And that is far more unsettling than a fantasy, because it suggests that even the leftover scraps of other systems may not resemble ours neatly. Comets in our solar system are often treated as time capsules. They preserve icy material from the early solar nebula, altered by heat, radiation, collisions, and orbital history. They carry clues about water, carbon compounds, and the cold regions where planets formed. When we study them, we are partly studying the childhood of the Sun's family. An interstellar comet may be a time capsule from a different childhood. Its ice formed under another radiation field. Its dust gathered in another disk. Its chemical inventory was shaped by another star's environment, another temperature history, another set of planetary disturbances. Even if the same physical laws apply, the initial conditions may be different enough to produce a chemical signature that feels foreign. This is where the word alien can be used carefully. Alien does not have to mean alive. It can simply mean not from here. An alien rock, alien ice, alien carbon chemistry, alien dust warmed by our sun for the first time after an unknowable journey. There is no need to invent intelligence when the natural object already expands the boundaries of our sample. And the sample is everything. Astronomy is often limited by distance. We infer, we calculate, we model. We use light as a messenger because we cannot hold distant galaxies, stars, or planets in our hands. But when an interstellar body enters the solar system, the universe briefly reduces the distance. Not enough for an easy landing mission, not usually enough for detailed sampling, but enough to aim telescopes, measure a coma, track outgassing, compare it with known comet behavior, and ask what kind of distant system might have launched it. That question connects back to the earlier unease. If early galaxies are richer and faster than expected, if planets are more common and diverse than expected, if atmospheres and possible habitability are harder to interpret than expected, then interstellar objects add a new layer. The galaxy is not only populated by distant systems, it is shedding pieces of them. The galaxy is exchanging fragments. Most of those fragments will never pass close enough to be seen. Space is too large. Our surveys are incomplete. The sky is wide. Objects are faint. And speed matters. Many interstellar visitors may cross the outer solar system invisibly. Some may pass behind the sun from our perspective. Some may be too dark, too small, or discovered too late. What we have found may be only the bright edge of a much larger population. That possibility is not frightening in the usual sense. It is unsettling because it reveals how little of the traffic we can see. Human beings tend to confuse detection with existence. Before we detect something, we imagine it is rare. After we detect a few examples, we realize the universe may have been doing it all along without our awareness. Exoplanets followed that pattern. So did gravitational waves. So did fast radio bursts. So may interstellar objects. First, one detection feels extraordinary. Then a second detection changes the category. Then the question becomes not whether they exist, but how many we have been missing. This is one of the quiet revolutions in modern astronomy. The universe is not changing. Our sensitivity is. Every improvement in sensitivity makes the cosmos seem busier. Not because it suddenly became crowded, but because the old silence was partly the silence of our instruments. When a new telescope, survey, detector, or algorithm opens a different window, it does not merely add facts. It reveals that the previous version of reality was incomplete. That can be difficult to absorb. For centuries, the sky looked stable. Stars moved in predictable patterns. Comets appeared as omens because their timing was not understood. Then, astronomy made them objects. Later, galaxies became islands of stars. Then the universe expanded. Then cosmic microwave background radiation became fossil light. Then dark matter and dark energy entered the map not as myths, but as names for measurable gaps in our explanation. Again and again. The cosmos did not become stranger because scientists became more dramatic. It became stranger because measurement improved. The same thing is happening now at the frontier of deep space. The evidence is more detailed than our emotional categories. A distant galaxy is not just far. It has a redshift, a luminosity, a stellar population estimate, dust uncertainties, possible emission lines, and a place inside a forming structure. An exoplanet is not just Earth-like. It has a radius, mass estimate, orbit, star type, irradiation level, density, possible atmosphere, and a long list of unknowns. A radio search is not just nothing. It has a sensitivity threshold, a frequency range, a time window, interference filters, and a statement about what was not found. An interstellar comet is not just weird. It has a trajectory, activity level, gas ratios, dust behavior, and chemistry shaped by a history we cannot reconstruct fully. The universe is turning adjectives into measurements. That is why the worry grows more sophisticated. It is not the fear of a single discovery. It is the recognition that our old words are too blunt. Empty is too blunt. Habitable is too blunt. Earth-like is too blunt. Silent is too blunt. Ancient is too blunt. Even deep space is too blunt, because it suggests one dark distance, when the reality is layers of time, matter, chemistry, and probability folded into one view. Scientists are trained to live with that complexity. But even within science, there are moments when the data press hard enough to change the atmosphere. A new galaxy forces revisions to early formation pathways. A new planet population changes how common certain architectures may be. A possible atmospheric molecule forces debates over false positives. A non-detection narrows a search space. A comet from another star hints at chemistry beyond our local inventory. Each result is careful. Each has caveats. Each can be argued, refined, weakened, or strengthened, but together they produce a clear message. The universe is not behaving like the simplified version humans carried into the space age. And maybe it never did. Maybe the simplified version was all we could hold before the evidence became this detailed. There is a strange comfort in that, if we let it settle. The discomfort does not come from the universe becoming more dangerous. It comes from the universe becoming more real. Real things have texture. They resist summary. They contain exceptions, edge cases, misleading first impressions, and patterns that only become visible after years of patient measurement. Deep space is becoming real in that way. Not a painted backdrop, not a mystical darkness, not a place where fantasies can survive untouched. A physical archive, filled with objects old enough to test cosmic history, worlds numerous enough to challenge our loneliness, signals absent enough to sharpen the silence, and fragments foreign enough to remind us that our solar system is not the whole laboratory. And as the archive opens, the human position inside it becomes less central. That may be the deepest reason these discoveries feel unsettling. They do not point toward one dramatic threat. They point toward a quieter demotion. Earth is not the only stage. The sun is not the only kind of system. Our planets are not the only planetary architecture. Our chemistry is not the only chemistry worth studying. Our silence is not the only possible silence. Our timeline is not the only way matter can organize itself into complexity. We are not being attacked by deep space. We are being corrected by it. And correction is not always dramatic while it is happening. Sometimes it happens quietly, inside a graph. A data point refuses to sit where the old expectation placed it. A spectrum shows a line that needs careful explanation. A galaxy appears in a region of time where it should be smaller, dimmer, or less chemically evolved. A planet population reveals that our own solar system is not the rule, but one possible outcome among many. A radio search reports no credible signal, and the absence is written down with enough detail to matter. This is how the universe changes us, not by shouting, but by becoming more specific. The more specific it becomes, the harder it is to hide inside vague wonder. Wonder is easy when the stars are only beautiful. Wonder becomes heavier when each point of light carries a measurement that can embarrass a theory, refine a probability, or remove a comfortable assumption. Deep space is not just a view anymore, it is a set of tests. And one of the hardest tests is time. Human beings are used to thinking in lifetimes. Civilizations, maybe written history if we stretch ourselves. Astronomy asks us to think in millions and billions of years, but even that can become abstract. We hear that a galaxy existed a few 100 million years after the Big Bang, and the number feels large because all cosmic numbers feel large. But in the history of the universe, a few 100 million years is childhood. It is early enough that every mature feature becomes a question. If a galaxy is bright, what powered it? If it contains many stars, how quickly did gas gather? If it shows signs of heavier elements, where were the earlier stars that made them? If dust is present, how did enough material cycle through stellar death so soon? If a black hole is active, how did it grow? If a dense group of galaxies appears, how did gravity build that environment so quickly? Each question is technical, but together they carry an emotional force. They make the young universe feel busy, not calm, not empty, not slowly waking up in the way our simple mental picture suggests. Busy, violent, productive, bright in places, already making the raw ingredients that later planets, atmospheres, oceans, and living chemistry would need. That does not mean every early galaxy is a crisis. Many results will be revised, some candidates will be downgraded, some apparent tensions will become ordinary once better models include bursty star formation, unusual stellar populations, lensing effects, dust behavior, or improved measurements. This is not a weakness of science, it is the process doing its job. But the deeper pattern remains. Every time our instruments reach farther, the early universe answers with more structure than our intuition expects. That word, intuition, is important. Scientists do not rely on intuition alone. They rely on evidence, equations, models, observations, and peer criticism. But even science has guiding pictures in the mind. A young universe should look young. A distant planet in the habitable zone should feel promising. A nearby system with rocky worlds should feel like a place worth listening to. A comet from another star should feel like a visitor carrying a story. Then the data arrive, and the picture changes. A young universe may look surprisingly developed. A habitable zone planet may have no atmosphere. A promising system may remain radio quiet. An interstellar comet may be chemically unfamiliar without being artificial. The universe keeps taking emotionally simple categories and filling them with physical complications. This is the true atmosphere of modern deep space research. It is not fear. It is the slow realization that reality has more mechanisms than our stories have room for. Consider the difference between distance and depth. Distance is a number. Depth is what happens when that number contains history. A galaxy 10 billion light years away is not merely far. It is being seen when the universe was younger. Its light has moved through expanding space. Its color has shifted. Its shape may be distorted. Its brightness may be affected by dust, gravitational lensing, or bursts of star formation. To understand it, scientists have to reconstruct a scene from evidence that has been stretched across time. That reconstruction is fragile and powerful at once. It is fragile because the data can be faint. Powerful because even faint data carry rules. Atoms absorb and emit light in particular ways. Gravity bends paths in particular ways. Expanding space stretches wavelengths in particular ways. A telescope does not need a galaxy to explain itself in human language. It only needs the galaxy's light to obey physics. And that may be the most astonishing part. A photon that began its journey before Earth existed can still arrive carrying information. It can still be counted. It can still land in a detector cold enough and sensitive enough to register its presence. It can still help reveal whether a galaxy contained certain elements, whether stars were forming rapidly, whether dust changed the color of the light, whether the object belongs to a population that our models must now explain. The universe is ancient, but it is not mute. It has been speaking in physics the whole time. Only now are we building instruments capable of hearing more of the sentence. And as that sentence lengthens, the old human comfort begins to weaken. We once imagined ourselves near the center. Then astronomy moved Earth away from the center of the solar system. Then the solar system away from the center of the galaxy. Then the galaxy into a universe of galaxies. Then visible matter into a cosmos dominated by dark matter and dark energy. Each step was not just scientific, it was psychological. Deep space discovery continues that tradition. It does not merely say Earth is small. We already know that. It says our examples are small. Our solar system is a small example of planetary architecture. Our atmosphere is a small example of atmospheric evolution. Our biology is a single example of life. Our technology is a brief example of intelligence. Our telescopes are young. Our searches are narrow. Our theories are powerful, but they are maps drawn from incomplete territory. That is a deeper demotion than size. It is a demotion of confidence. And yet, it is also the beginning of a more mature kind of wonder. A childlike wonder says, "The universe is huge." A more difficult wonder says, "The universe is specific, and its specifics do not exist for us." A galaxy does not form early to surprise us. A planet does not lose its atmosphere to disappoint us. A radio signal does not fail to appear in order to deepen our loneliness. An interstellar comet does not pass through the solar system as a message. These things happen because matter follows rules under conditions more varied than our experience. The universe is not trying to be mysterious. Mystery is what we feel when reality exceeds our current instruments and concepts. That is why the best scientists are often careful with language. They know that words can make the unknown smaller than it is. Impossible can become a trap. Earth-like can become a sales pitch. Habitable can sound more certain than it is. Signal can become a magnet for fantasy. Alien can make chemistry sound like intelligence. Worry can make disciplined uncertainty sound like panic. But behind the careful language, the tension is real. There are still too many open questions at once. How fast did the first galaxies assemble? How did the first heavy elements spread? Did early black holes grow from massive stellar remnants, direct collapse gas clouds, or something more complex? Why do some planet types appear common elsewhere but absent here? How often do rocky planets keep atmospheres around small stars? How often does chemistry cross into life? How often does life become detectable? How often does intelligence produce signals that another species could recognize? How many interstellar objects pass unseen through the solar system each year? None of these questions requires fear to be powerful. Their power comes from the fact that they are becoming answerable. That is the part we are living through now. Not the age when people first wondered whether other worlds existed. Not the age when galaxies were first recognized as distant systems. Not the age when radio astronomy opened invisible skies. We are living in an age when different kinds of evidence are beginning to overlap. Early galaxies tell us how quickly matter became complex at cosmic scale. Exoplanets tell us how common and varied planetary systems are. Atmosphere studies tell us that distant worlds are not just dots, but environments. SETI searches tell us how limited, careful, and difficult the search for technology really is. Interstellar objects tell us that other systems can physically contribute material to our own sky. Individually, each frontier has uncertainty. Together, they suggest that deep space is no longer a distant category. It is an archive with many shelves, and we have only just learned how to read the labels. That archive does not guarantee comfort. A more complete universe may not be a friendlier one. It may tell us that life is rare, or common but mostly microbial, or common but usually hidden under ice, or intelligent only for brief windows, or detectable only by methods we have not invented. It may tell us that galaxies formed efficiently in ways our models missed, or that early black holes grew faster than expected, or that planetary systems often destroy their best chances before life can begin. Any of those answers would change the way humanity sees itself, but the absence of an answer changes us too, because uncertainty at this scale is not empty. It is charged. It means we are standing between old ignorance and future knowledge, close enough to see outlines, but not close enough to resolve the shape. That is why the discoveries feel uncomfortable. We can no longer pretend the questions are philosophical only. They are observational now. They have coordinates, spectra, catalogues, limits, and error bars. The unknown has become measurable, and once the unknown becomes measurable, it becomes harder to ignore. This is what deep space is doing to science, turning ancient human questions into technical work. Are we alone? Becomes a search strategy. Where did complexity begin? Becomes a redshift survey. How common are worlds? Becomes a transit catalogue. What are other systems made of? Becomes comet chemistry and atmospheric spectroscopy. How much do we not see? Becomes a question for next generation surveys. The romance is still there, but it has changed. It is no longer the romance of staring upward and imagining anything. It is the romance of being corrected by evidence so faint that it takes a space telescope, a giant radio dish, or a global network of observatories to catch it before it disappears into noise. That kind of romance is harder. It does not flatter us, but it is more honest, and honesty may be the real source of the worry. Deep space is forcing science to admit that many of its strongest models are still being tested at their edges. It is forcing the public to admit that exciting does not mean confirmed. It is forcing anyone who cares about life beyond Earth to admit that abundance and evidence are not the same thing. It is forcing us to distinguish between a clue, a candidate, a detection, a hypothesis, and a discovery. Those distinctions are not boring. They are the guardrails that keep awe from turning into misinformation. Because the real universe does not need exaggeration. It already contains galaxies whose light began before the solar system existed, planets that orbit stars we will never visit, atmospheres we can read only through missing colours, silent systems that sharpen the loneliness question, and interstellar fragments that pass through our neighborhood, carrying chemistry from elsewhere. If that is not enough, then the problem is not the universe. The problem is that we have forgotten how strange truth can be, and the strangest truths often need no decoration. A galaxy too bright for its age does not need to be called impossible. It is already disturbing if it simply asks the model to work harder. A planet does not need to be called Earth's twin. It is already profound if it shows us that rocky worlds are common, but habitability is fragile. A quiet radio observation does not need to be sold as cosmic loneliness. It is already meaningful if it tells us what kind of signal was not there. An interstellar object does not need to be turned into a machine. It is already astonishing if it formed around another star and wandered into the reach of our telescopes. The more carefully we speak, the more powerful the discoveries become. This is why the language of modern astronomy can seem restrained on the surface, while carrying enormous consequences underneath. A paper may say that an observation challenges existing models, or that a result is consistent with rapid early formation, or that no credible technosignature candidate was found. These phrases do not sound cinematic, but each one is a door. Behind rapid early formation is the question of how the first galaxies grew. Behind atmospheric candidate is the question of whether chemistry can reveal life from light years away. Behind non-detection is the question of whether our search is too narrow, too early, too weak, or aimed at the wrong kind of signal. Behind interstellar origin is the realization that the solar system is not isolated from the debris of other stars. Science uses careful words because the universe punishes careless ones. But the careful words do not make the universe smaller. They make the mystery harder to dismiss. A sensational claim can be rejected quickly. A careful measurement stays, and the measurements are beginning to form a chain. The first link is the early universe, where the timeline itself is under pressure. If luminous galaxies and heavy element signatures appear very early, then star formation, gas collapse, and enrichment may have worked more efficiently in some places than our older, simplified pictures suggested. That does not erase the Big Bang. It refines what happened after it. It asks how quickly the raw universe learned to build complexity. The second link is the planet population, where our solar system has lost its status as the obvious template. We have found worlds that orbit too close. Worlds larger than Earth but smaller than Neptune. Worlds in compact chains. Worlds around small red stars. Worlds around multiple stars. Worlds whose atmospheres are being stripped. Worlds that may be ocean-rich, lava-covered, airless, cloudy, or hidden behind chemistry we barely know how to read. The third link is the search for life, where the evidence is not absent but incomplete. Chemistry can be suggestive without being decisive. A gas can be exciting in one environment and ordinary in another. A promising planet can become less promising when the star's behavior is understood. A possible biosignature can become a false positive. This does not weaken the search, it makes it more serious. The fourth link is the search for technology, where silence has become something measured rather than imagined. There is a difference between never listening and listening carefully within a defined range. Modern searches do not settle the cosmic question, but they give it shape. They say, not this frequency, not this strength, not this window, not this obvious kind of beacon. The fifth link is interstellar matter, where distant planetary systems are no longer only inferred from light. Their debris can cross our orbit. Their chemistry can briefly become accessible. Their fragments can remind us that the galaxy is a physical environment, not just a background image. When those links are seen together, the title begins to make sense. Scientists are starting to worry, not because deep space has revealed a single nightmare, but because it is revealing a universe that is active at every scale we examine. Early galaxies are active, planet formation is active, atmospheric chemistry is active, search limits are active, interstellar exchange is active. The old picture of deep space as a cold, empty, distant stage is no longer enough. It is not empty. It is not simple. It is not finished being understood. And maybe, most importantly, it is not arranged around our expectations. That last idea is the one that keeps returning. Humans are pattern-making animals. We want the universe to have a story shape. Beginning, middle, meaning. We want early galaxies to be primitive, planets to sort neatly into habitable and uninhabitable, life to leave clear fingerprints, intelligence to announce itself, and interstellar visitors to fit into familiar categories. We want the cosmos to be difficult, but not too difficult. The actual cosmos appears to be more patient and less cooperative. It gives us galaxies that may need new formation pathways. It gives us planet categories missing from our home system. It gives us atmospheric clues that require years of caution. It gives us silence where imagination expected messages. It gives us natural visitors strange enough to inspire speculation, then asks science to separate wonder from wishful thinking. That separation may be the central discipline of our time. Wonder without discipline becomes fantasy. Discipline without wonder becomes paperwork. The best astronomy needs both. It needs enough wonder to ask questions that seem too large for one lifetime, and enough discipline to accept that most answers arrive slowly, in fragments, with error bars attached. It needs the courage to be surprised, and the restraint not to declare victory too early. It needs public excitement, but not public deception. It needs mystery, but not manufactured mystery. Deep space is giving us more than enough real mystery. One real mystery is why some early galaxies appear so luminous so soon. Another is how common truly Earth-like conditions are among the thousands of known planets. Another is whether life, once begun, is easy to detect across interstellar distance. Another is why, in a galaxy so old and planet-rich, no technological signal has become undeniable. Another is how many interstellar objects pass unseen, carrying the chemistry of stars we have never named. These are not small questions. They are the kind of questions that can change humanity without ever producing a dramatic explosion, invasion, or final revelation. They change us by making the familiar universe harder to believe in, not the real universe, but the familiar version, the simple one, the one where deep space is mostly absence and Earth is the natural reference point. That version is fading. In its place is a universe with too much evidence to be romanticized casually, and too many unknowns to be reduced to slogans. This is why the phrase, "scientists are worried," has to be handled carefully. The worry is not helplessness. It is responsibility. It is what serious people feel when the evidence begins to outgrow the old frame, but the new frame is not yet complete. It is the pressure of knowing that one wrong public claim can mislead millions, but one cautious discovery can still reshape a field. In astronomy, worry often looks like more observing time. It looks like follow-up spectroscopy. It looks like independent teams checking the same object. It looks like simulations being rebuilt with different assumptions. It looks like telescopes returning to a planet during another transit. It looks like radio data being cleaned again for interference. It looks like survey strategies designed to catch the next fast-moving interstellar object earlier, while it is still bright enough to study. This is not panic. This is science taking the universe seriously, and maybe that is more unsettling than panic would be. Panic burns out quickly. Serious attention does not. It accumulates. It revisits. It corrects itself. It refuses the easy sentence. It keeps listening after silence. It keeps measuring after surprise. It keeps asking whether the strange object is truly strange, or whether our sample was simply too small. That question, whether our sample was too small, may explain almost everything. Our sample of galaxies was too shallow before better infrared telescopes. Our sample of planets was one solar system before exoplanet surveys. Our sample of atmospheres is still tiny. Our sample of life is one biosphere. Our sample of technology is one species, broadcasting and listening for only a brief moment. Our sample of interstellar objects is still only a handful. Again and again, humans build conclusions on small samples, because small samples are all we have. Then instruments improve, the sample grows, and the universe reminds us that confidence was premature. There is humility in that, but also danger. not physical danger from deep space. At least, not in the sense the title might suggest. The danger is intellectual. The danger is clinging to old certainty because uncertainty feels uncomfortable. The danger is turning every clue into proof, or every silence into despair, or every anomaly into conspiracy. The danger is losing the ability to stand in the middle, where the real work happens. The middle is where modern astronomy lives, between the first light and the mature galaxy, between a planet and a home, between chemistry and life, between silence and absence, between a natural interstellar object and the fantasies projected onto it, between what our models explain and what the next observation may force them to explain better. That middle space is not weak. It is where discovery has always lived, before becoming textbook knowledge. There was a time when galaxies beyond the Milky Way were debated, a time when planets around other stars were hypothetical, a time when gravitational waves were mathematical predictions, a time when black holes were strange solutions, not photographed shadows, a time when the cosmic microwave background had not yet become the oldest light we could map. The frontier always feels unstable from inside it. Later, it becomes history. Right now, deep space feels unstable because the frontier has widened in several directions at once. We are not only looking farther, we are looking earlier, fainter, colder, redder, faster, and more chemically. We are reading light that has been stretched by cosmic expansion. We are watching stars blink as planets cross them. We are listening for engineered narrowband signals while surrounded by human interference. We are tracking objects moving on hyperbolic paths through the solar system. We are asking whether a small spectral feature is a molecule, a cloud, a stellar artifact, or the beginning of something larger. This is not one discovery, it is a change in human reach, and every change in reach changes what can surprise us. A person with the naked eye is surprised by a comet. A person with a telescope is surprised by moons around Jupiter. A person with radio astronomy is surprised by pulsars. A person with space telescopes is surprised by galaxies at the edge of time. A person with exoplanet spectra is surprised by atmospheres around worlds that no one will touch. A person with all sky surveys is surprised by visitors from other stars. The universe did not become more populated. Our reach became less blind. That may be the most important idea to carry forward. Deep space has always contained more than we could see. The worrying part is not that new things suddenly appeared. It is that they were always there, and we are only now becoming responsible for understanding them. And responsibility begins with admitting how easily the mind reaches for the wrong explanation. When something in deep space looks unusual, the first temptation is to make it meaningful in human terms. A strange object becomes a visitor. A silent system becomes loneliness. A possible atmospheric molecule becomes life. A distant, bright galaxy becomes broken physics. A fast-moving interstellar body becomes a message. The human imagination wants every anomaly to face us. But most anomalies are not about us. They are about incomplete samples, better instruments, rare conditions, or natural processes unfolding in environments we have never personally encountered. This does not make them less fascinating. It makes them more difficult. And difficulty is where the real awe begins. Take the early galaxies again. Their challenge is not that they are impossible, but that they force a better accounting. How did dark matter halos gather enough material? How did gas cool efficiently? Were the first stars different from later ones? Did bursts of star formation make some galaxies temporarily brighter than expected? Did black holes contribute to the light? Did dust hide or exaggerate parts of the picture? Are we seeing rare overachievers because the brightest objects are the easiest to detect? Each possibility is less dramatic than science is broken, but each one opens a real scientific path. That is how a field matures. It does not merely collect surprises, it sorts them. Some surprises vanish under better data. Some become known classes. Some remain stubborn. Some turn into new physics. But only after ordinary explanations have been exhausted. Most of the time, The universe teaches us by being complicated within the rules we already know. That is not disappointing. It is profound. A universe that obeys rules and still exceeds expectation is more powerful than a universe that simply breaks rules whenever we are bored. The first can be studied. The first can be understood in layers. The first can humble us without surrendering to fantasy. The same discipline applies to planets. A planet in a habitable zone is not a promise. It is an invitation to ask better questions. Does it have an atmosphere? Has that atmosphere survived stellar radiation? Is there surface pressure? Is water stable there now, or was it lost long ago? Does the star flare violently? Is the planet tidally locked? Does its interior recycle carbon? Does it have clouds that alter its temperature? Does the atmosphere show molecules that belong together in a way that needs explanation? The phrase habitable zone can sound warm and hopeful. In reality, it is a rough geometric starting point. It mostly says that, under the right atmospheric conditions, liquid water could be possible at the surface. It does not say liquid water exists. It does not say life exists. It does not even say the planet is comfortable. Venus sits near a region where sunlight could sound promising in a simplified story, yet its surface is hot enough to melt lead. Crushed beneath a thick carbon dioxide atmosphere, Mars lies farther out, with evidence of ancient water, but today it is cold, dry, and exposed. Even in our own solar system, distance from the Sun is not destiny. That lesson becomes sharper around other stars. Small red dwarfs are common, which makes them attractive targets in the search for rocky planets. Their dimness makes habitable zone orbits close in, and close-in planets are easier to detect by transit. But those same stars can be active. Flares and high-energy radiation may erode atmospheres. Tidal locking may produce permanent day and night sides, though atmosphere and ocean circulation could complicate that picture. Nothing is simple enough for hope alone, so when scientists study systems like TRAPPIST-1, the public may see a cluster of possible Earths, while researchers see a much more demanding problem: star activity, planetary densities, atmosphere retention, orbital resonances, possible volatile loss, observational limits, and the long challenge of distinguishing a real atmospheric signal from noise. The wonder survives, but it becomes more disciplined, and that discipline is essential, because deep space has a way of punishing emotional shortcuts. If we call every interesting planet Earth-like, then the word loses meaning. If we call every possible atmospheric clue life, then actual life, if we ever find it, will arrive into a world already tired of false alarms. If we call every silence proof, then we misunderstand what searching means. If we call every strange interstellar object artificial, then we fail to appreciate what natural planetary systems can produce. The universe does not need our shortcuts. It needs patience. Patience is difficult because the scale is painful. The galaxy may contain hundreds of billions of stars. Many stars may have planets. Some planets may be rocky. Some may have atmospheres. Some may have water. Some may have chemistry that grows complex. But every sum hides a fraction we do not yet know. A tiny change in those fractions can transform the meaning of the galaxy. If life begins easily, wherever conditions allow, then the Milky Way may be biologically active in ways we have not detected. If life is rare even under good conditions, then Earth becomes a far more unusual event. If simple life is common, but complex life is rare, then the galaxy may be full of microbes and almost empty of minds. If intelligence appears but seldom develops technology, the silence makes sense. If technology appears but does not last, then timing becomes the barrier. If intelligence avoids detectable broadcasting, then our searches may miss what matters. The deepest uncertainty is not one number, it is a chain of numbers. How many stars have planets? How many planets are rocky? How many keep stable environments? How many develop life? How many develop complex life? How many develop intelligence? How many create detectable technology? How long does that detectable phase last? How many signals cross our instruments during the short window in which humans are listening? This is why silence cannot be interpreted casually. A silent sky may mean we are alone. It may mean life is rare. It may mean intelligence is rare. It may mean technology is brief. It may mean signals are not aimed at us. It may mean they use physics or methods we are not searching for. It may mean civilizations are too far apart in time. It may mean we have barely begun. The honest answer is not dramatic. The honest answer is that silence has many causes, and until we can separate them, the silence remains one of the most powerful findings in deep space. It is not a discovery of nothing. It is a discovery of limits, our own limits, limits of sensitivity, imagination, time, and method. It tells us that the universe is not obligated to answer the first way we ask. That may sound simple, but it cuts deeply into human expectation. We are used to technology making things immediate. Send a message, get a reply. Search a database, get a result. Point an instrument, reveal the secret. The cosmos does not work on that schedule. A radio wave from a civilization 1,000 light-years away would take 1,000 years to reach us. A reply would take another 1,000. A civilization could rise, flourish, turn inward, change communication methods, or vanish before the conversation even began. A planet could be alive for billions of years without producing anything detectable across interstellar distance. A biosphere could be hidden under ice. A technological species could be quiet by choice, necessity, or indifference. Deep space forces us to think in delays. The light we see from distant galaxies left before Earth existed. The planets we detect may be worlds as they were years, decades, or centuries ago, depending on distance. The signals we search for, if any exist, are messages from another time. Even interstellar objects are old travelers, carrying histories that began long before they entered our neighborhood. Everything arrives late. That lateness changes the meaning of discovery. We are not looking at the universe as it is right now, in one universal present. We are receiving layers of old information, ancient galaxy light, starlight filtered through planetary atmospheres, radio silence from a window already closed, cometary ice warmed now, but formed elsewhere long ago. The sky is less like a live broadcast and more like an archive, where every shelf belongs to a different era. This is one reason the findings feel eerie. They do not simply show distance, they show delay. And delay means separation. We may find a galaxy as it was near the beginning of time, but it is not that galaxy anymore. We may examine a planet around a nearby star, but even nearby means the information has travelled. We may listen for technology, but any signal would be a fossil of another civilization's moment. The universe is full of fossils made of light. Some are beautiful. Some are troubling. All of them are incomplete. And yet, incomplete evidence is not weak evidence. It is the only kind astronomy often has. The skill lies in knowing how much weight each clue can carry. A spectrum can reveal a molecule, but not the whole weather of a world. A redshift can place a galaxy in time, but not automatically give its full mass history. A radio non-detection can constrain a signal type, but not settle the existence of intelligence. A comet's outgassing can reveal chemistry, but not the complete birthplace of the object. Every finding has a boundary. Science advances by drawing those boundaries honestly. That honesty may be the real difference between fear and worry. Fear leaps beyond the boundary. Worry studies it. Fear says the strange object must be artificial. Worry asks whether the trajectory, brightness, outgassing, and composition fit natural possibilities. Fear says an early galaxy breaks everything. Worry asks which assumptions about star formation need revision. Fear says a silent star system proves nobody is there. Worry asks what kinds of signals the search could actually detect. Worry is slower than fear, but it leaves knowledge behind. And right now, deep space is producing exactly the kind of evidence that deserves worry in that disciplined sense. Not because it threatens Earth, but because it threatens lazy certainty. It forces scientists to keep separate what is known, what is suspected, what is possible, and what is still speculation. It forces the public to accept that the most important discoveries may arrive without a simple headline. That is hard in an age built for instant conclusions. A telescope image appears, and within hours people want meaning. A preprint claims a distant galaxy, and people want a revolution. A molecule is discussed in an exoplanet atmosphere, and people want life. A new interstellar object is found, and people want intention. But reality often moves through correction. The first report is tested, the data are reprocessed, other teams disagree, instruments return for another look, claims become narrower. Sometimes the excitement fades, sometimes it grows. This is not confusion. This is the cost of being careful at the frontier. And the frontier is expanding faster than our instincts can adapt. We are not built to intuit redshift 14. We are not built to feel what 300 million years after the Big Bang really means. We are not built to imagine a planet locked in close orbit around a small star, with one hemisphere facing permanent light and the other permanent dark. We are not built to understand how a molecule's absorption feature can be both exciting and ambiguous. We are not built to emotionally process a silence measured across stars. So we reach for stories. Science must reach for evidence. The tension between the two is where the modern cosmic documentary lives. The story must be strong enough to carry the viewer, but honest enough not to deform the science. The evidence must be clear enough to matter, but human enough to be felt. The mystery must remain mystery where it is truly unresolved, not be inflated into certainty. That balance is difficult, because the subject is genuinely overwhelming. Deep space now contains early galaxies that challenge formation timelines, planet populations that challenge our solar system bias, atmospheric studies that challenge our definition of habitability, radio searches that challenge simple ideas of contact, and interstellar objects that challenge the imagined isolation of our system. Each frontier tells the same quiet lesson. We are still early, not early in cosmic time, but early in understanding. Early in exoplanet atmospheres, early in interstellar object statistics, early in technosignature searches, early in mapping the first galaxies with high confidence, early in learning which cosmic surprises are rare exceptions and which are signs of a larger pattern. That may be the most unsettling discovery of all. After centuries of astronomy, after space telescopes, planetary probes, equations, simulations, detectors, and sky surveys, we are still at the beginning of the real inventory. The universe is not running out of mystery. It is becoming measurable enough to multiply it. And if mystery is multiplying, then the question becomes whether our tools can keep up with it. For centuries, the answer was no. The universe was always richer than our ability to measure. Ancient starlight crossed space with information inside it, but our eyes could not separate the message. Planets tugged on stars, but the motion was too small. Atmospheres filtered light, but the change was too faint. Interstellar objects moved through darkness, but surveys were too limited to catch most of them. The sky was never simple. It only looked simple because we were under-equipped. Now that is changing. A modern observatory is not just a larger eye. It is a machine for turning almost nothing into evidence. A few photons become a spectrum. A tiny dip in brightness becomes a planet candidate. A slight wobble becomes a mass estimate. A faint infrared smudge becomes a galaxy near the cosmic dawn. A moving point becomes an orbit that says this object does not belong to the sun. That transformation is one of the most beautiful things human beings do. We take weakness and make it measurable. But the cost of better measurement is that the universe becomes less emotionally manageable. Every new layer of sensitivity reveals a deeper layer of complication. A telescope built to find the first galaxies finds them, but then the galaxies look more numerous, brighter, or more chemically interesting than expected. A survey built to find planets finds thousands, but then the planets reveal types and arrangements our own solar system never prepared us for. A radio telescope built to listen finds no clear signal, but then the silence itself becomes more precise and harder to shrug away. This is why progress can feel like unease. A less capable civilization can keep cleaner myths. A more capable civilization has to live with messier evidence. And messy evidence is exactly what we should expect if we are finally studying the universe at its real scale. The cosmos is not a classroom diagram. It is not built from representative examples placed neatly in order. It is a history of collisions, collapses, radiation fields, rare alignments, violent births, quiet failures, chemical accidents, and enormous stretches of time. It contains patterns, but also exceptions. It contains laws, but also extreme environments where those laws produce unfamiliar outcomes. The early universe is messy because gravity does not wait for human intuition. Dense regions collapse, gas cools, stars ignite, massive stars live quickly and die violently. Black holes may grow inside crowded young systems. Radiation can both create and suppress further star formation. Dust can hide light or change how we interpret it. A galaxy that looks too bright may be a clue about stellar populations, or starbursts, or lensing, or incomplete models, or some combination of all of them. The planet population is messy because formation is not gentle. Young disks are turbulent. Worlds migrate. Giants scatter smaller bodies. Atmospheres escape. Moons collide. Planets lock into resonances. Some systems become compact and orderly. Others become sparse and violent. Some worlds keep thick envelopes of gas. Others are stripped down to rock. Some may hold water for billions of years. Others may lose it before life has a chance to begin. The search for life is messy because life, if it exists elsewhere, may not advertise itself in the way we want. It may be microbial, buried, seasonal, rare, or chemically subtle. It may change an atmosphere slowly. It may live under ice, away from direct view. It may leave clues that can be mimicked by geology or sunlight. It may exist on worlds whose signals are too small for our present instruments. It may be abundant and still hard to prove. The search for intelligence is messier still, because intelligence is not only biology. It is behavior, culture, technology, choice. A civilization might broadcast loudly or not at all. It might use narrow beams, optical pulses, spread spectrum signals, neutrino communication, artifacts, megastructures, or methods we have not imagined. It might last long enough to be common in principle, but rare in the same moment we are listening. It might be nearby in space and distant in time. That is the trouble with deep space. Distance is only one kind of separation. There is also separation by era, by chemistry, by environment, by method, by assumption. A signal can miss us because it was sent before humans existed. A biosphere can hide because its atmosphere is ambiguous. A galaxy can confuse us because the stars inside it are unlike the stars we use as templates. An interstellar object can pass unseen because it is too dark against the sky. The universe is full of ways to be real without being obvious. That sentence may be the key to the whole story. Real does not mean obvious. For most of history, exoplanets were real without being obvious. Gravitational waves were real without being obvious. The cosmic microwave background was real without being recognized. Interstellar visitors were possible before we confirmed them. The first galaxies existed before we had instruments to see them. The universe does not wait for detection to become true. Detection only changes us. It moves an idea from imagination into responsibility. Once an object is detected, it must be measured. Once it is measured, it must be interpreted. Once it is interpreted, it must be compared with models. Once it pressures a model, the model must either adapt or fail. This is the slow machinery beneath every dramatic headline. It is not glamorous from the outside, but it is the part that matters most. And it is also where humility enters. Humility is not saying we know nothing. That would be false. We know an extraordinary amount. We know the universe is expanding. We know light has a finite speed. We know stars manufacture heavy elements. We know galaxies evolve. We know planets are common. We know chemistry is widespread. We know life has emerged at least once. We know intelligence can build instruments capable of reading ancient light. Humility is knowing that each of those truths opens further uncertainty. The universe expands, but dark energy remains one of the deepest mysteries in physics. Stars make elements, but the earliest enrichment history is still being reconstructed. Galaxies evolve, but the details of the first luminous systems remain under pressure. Planets are common, but habitable planets are not yet counted with confidence. Chemistry is widespread, but life is unconfirmed beyond Earth. Intelligence exists here, but its cosmic frequency is unknown. The known and the unknown are not enemies. They are connected. Every real discovery increases both. That is why scientists can be excited and worried at the same time. Excited because the instruments are working. Worried because the data are forcing sharper questions than the old frameworks can comfortably absorb. Excited because early galaxies are being seen. Worried because their formation histories may not be simple. Excited because thousands of exoplanets are known. Worried because the path from planet to life remains brutally unclear. Excited because SETI searches are more disciplined. Worried because silence is becoming better measured. Excited because interstellar objects can be studied. Worried because we may be seeing only a tiny, biased sample. This combination may look contradictory from the outside. It is not. It is what serious discovery feels like. A field that is only confident is probably not near its frontier. A field that is only confused has not built enough tools. A field that is both confident and unsettled is often standing exactly where new knowledge is forming. Deep space astronomy is standing there now, and the next tools may make the unease stronger, not weaker. Future observatories will find more distant galaxies, more faint objects, more planets, more atmospheric spectra, more transient events, and possibly many more interstellar visitors. Better surveys may catch fast-moving objects earlier. More sensitive telescopes may test whether rocky planets around small stars keep atmospheres. Larger datasets may reveal whether early bright galaxies are rare outliers or signs of a broader pattern. Improved radio and optical technosignature searches may push silence into narrower corners. This means that the next generation of astronomy may not give us one grand answer. It may give us better questions in every direction, and that is what mature science often does. It turns broad mystery into detailed mystery. It replaces, "Are there other worlds?" with, "What kinds of worlds? Around which kinds of stars? With which atmospheres? Under which histories?" It replaces, "Are we alone?" with, "What forms of life? At what detectability? Over what timescale? With what false positives?" It replaces, "How did galaxies form?" with, "Which feedback processes? In which environments? At which redshifts? Under which assumptions?" The mystery does not disappear. It becomes structured. A structured mystery is more useful than a vague one, but it is also harder to live with. A vague mystery can hold any dream. A structured mystery tells you where your dream is unlikely. It tells you which doors are narrowing. It tells you which claims have failed. It tells you which hopes require better evidence. It removes the comfort of infinite possibility and replaces it with constrained uncertainty. That is exactly what is happening with deep space. The universe remains enormous, but not blank. Unknown, but not shapeless. Strange, but not lawless. Silent, but not meaningless. Filled with worlds, but not automatically filled with life. Filled with ancient light, but not automatically arranged to fit our timelines. Filled with fragments from other stars, but not automatically carrying intention. This is a harder universe than the one imagined by simple wonder. It is also a better one, because a universe that can correct us can teach us, and the teaching has already begun. It teaches that early complexity may arise faster than intuition expects. It teaches that planetary systems are not variations on our own, but a vast family of outcomes. It teaches that atmospheric chemistry is a language with false friends and difficult grammar. It teaches that silence must be measured before it can be interpreted. It teaches that the solar system sits inside a galaxy where matter can travel between stars, rarely but meaningfully. Most of all, it teaches that human expectation is not a scientific instrument. Expectation can guide questions, but it cannot decide answers. No amount of longing can make a biosignature real. No amount of discomfort can make a galaxy disappear. No amount of skepticism can erase a confirmed planet. No amount of imagination can turn a natural object into technology. The universe is not negotiated by our feelings. It is met by evidence, and evidence, when it is honest, often leaves us with a strange emotional mixture, smaller and more privileged at once. Smaller because Earth is less central than ever. More privileged because we live at a moment when ancient photons, distant planets, silent searches, and interstellar fragments are all becoming accessible to human inquiry. That combination is rare. For most of life on Earth, the universe was overhead and unreachable. For most of human history, it was visible but unreadable. Now, briefly, one species has learned to build instruments that can turn deep time into data. We can look at the glow of a galaxy from near the cosmic dawn. We can infer planets by watching stars dim. We can search for technology around systems we will never visit. We can notice an object that does not belong to the Sun and follow it as it crosses the inner solar system. There is no guarantee that we will understand everything we find. There is only the responsibility to look carefully. And perhaps that is why the discoveries feel heavy. Not because they bring doom, but because they bring obligation. Once deep space becomes measurable, ignorance is no longer as innocent as it was. We cannot pretend the questions are unknowable in the old way. Some are becoming knowable, slowly, partly, with uncertainty, but knowable enough that we must be careful with them. That carefulness is the opposite of fear. It is the beginning of wisdom. Wisdom, in this context, does not mean pretending we are detached. No one who studies deep space is truly detached from it. The work may be technical, but the implications are too large to remain purely technical. When a galaxy is seen near the beginning of cosmic history, it is not only a data point, it is a reminder that the universe had a life before every planet we know. When a planet is detected around a distant star, it is not only a signal in a catalogue, it is a possible environment, shaped by physics we may never witness directly. When a radio search finds no credible signal, it is not only an absence, it is a boundary drawn around one version of hope. The emotional weight comes from the fact that every measurement touches an old human question. Where did structure begin? How common are worlds? Is life a local accident or a cosmic habit? Can intelligence survive long enough to be found? Does the universe contain company or only echoes? These questions are ancient in spirit, but modern in method. A person thousands of years ago could wonder about the stars. A person today can wonder with instruments capable of testing parts of the question. That difference changes everything. Wonder becomes work. Curiosity becomes observing time. A dream becomes a spectrum. And spectra are unforgiving. They do not care what we hope to find. They contain absorption lines, emission lines, noise, contamination, and uncertainty. They reveal molecules when the data are strong enough, and mislead us when we ask too much of them. A spectrum is not a prophecy. It is a physical trace. It has to be earned, cleaned, compared, and challenged. This is why the search for life beyond Earth may be slower than the public expect. The first persuasive evidence may not look like a dramatic announcement. It may look like years of repeated measurements. A planet observed during multiple transits. A molecule detected by one instrument and then tested by another. False positive scenarios eliminated one by one. The star understood better. The planet's mass and radius improved. Clouds modelled. Temperature constrained. Alternative chemistry examined. The claim narrowed until it can stand. That process may feel frustrating from the outside, but it is exactly what would make the discovery real. Life beyond Earth, if ever detected remotely, will require more than excitement. It will require a web of evidence strong enough to survive doubt. And doubt, in science, is not the enemy of discovery. Doubt is the tool that keeps discovery from becoming wishful thinking. The same is true for intelligence. A candidate signal is not contact. A narrowband feature is not automatically technology. A strange pulse is not automatically a message. Human interference is everywhere. Satellites, aircraft, ground transmitters, electronics, reflections, software artifacts, and natural astrophysical sources can all create confusion. The history of signal searches is full of moments that seemed strange until the cause became ordinary. This does not make the search foolish. It makes the search difficult, and difficult searches require emotional discipline. They require scientists to be excited enough to notice anomalies and skeptical enough not to worship them. They require a willingness to follow a strange clue without promising the public that the clue has already become an answer. That discipline is part of what makes the current era so compelling. We are no longer asking whether the universe has surprises. It clearly does. We are asking which surprises are temporary, which are deep, and which reveal a new layer of reality. Some early galaxy tensions may soften with better data. Some exoplanet hopes may fade when atmospheres are lost or molecules are reinterpreted. Some interstellar objects may turn out to be chemically unusual but dynamically ordinary. Some silence may remain silence only because our search methods are narrow, but a few clues may endure. A few may become landmarks. That is how science often advances. Not every anomaly becomes a revolution. Most do not. But the process of testing anomalies strengthens everything around them. Even when a strange result disappears, we learn how instruments behave, how models fail, how biases enter, how assumptions mislead. A vanished anomaly can still improve the science. Deep space is full of these lessons now. The early universe frontier is teaching us how hard it is to infer mass, age, and star formation from faint ancient light. The exoplanet frontier is teaching us how bias detection methods can shape our view of what kinds of planets are common. Transit searches favor planets whose orbits cross in front of their stars from our perspective. Radial velocity searches favor planets massive enough or close enough to tug their stars detectably. Direct imaging favors young, bright, distant giant planets separated from their stars. Every method sees a different slice of the population. So even the census of worlds is not a simple list. It is a list shaped by how we are able to look. That matters because a biased sample can create a biased imagination. If we find many close-in planets, it may partly be because close-in planets are easier to detect. If we find large planets first, it may be because large planets make louder signals. If rocky worlds around small stars become central targets, it may be because their transits are easier to observe, not because they are the only worlds that matter. The universe we know is always partly the universe our instruments are tuned to reveal. This is a profound limitation. It means every discovery comes with a shadow, the things we are not yet able to see. And the shadow may be enormous. There may be Earth-sized planets in wider orbits that are difficult to detect. There may be quiet biospheres on worlds whose atmospheres are beyond our current reach. There may be interstellar objects too small or dark for present surveys. There may be early galaxies too faint to appear in current deep fields. There may be technosignatures that do not resemble narrowband radio transmissions at all. The unknown is not just beyond the horizon, it is between our methods. That idea should make us careful when we claim the universe is silent, empty, rare, common, young, mature, hostile, friendly, lonely, or crowded. The truth may depend on which window we are looking through. Infrared astronomy reveals one universe, radio astronomy reveals another, transit photometry reveals another, spectroscopy reveals another, gravitational waves reveal another. Each window is real, but none is complete. Deep space is not one picture. It is a composite we are still assembling. And as the composite grows, the human story changes. Once, we looked up and saw fixed stars. Then we saw a solar system. Then a galaxy. Then galaxies beyond the galaxy. Then an expanding universe. then cosmic background radiation, then black holes, dark matter, dark energy, exoplanets, interstellar visitors, and ancient galaxies near the edge of time. Each expansion did not only add objects, it changed the meaning of being human. The current expansion is especially intimate because it touches life. Galaxies are grand, but planets are personal. Atmospheres are personal. Water is personal. Chemistry that might resemble the preconditions for biology is personal. Silence from another system is personal because it brushes against our oldest fear, that consciousness may be rare. This is why the exoplanet frontier carries emotional force beyond its data. 1,000 gas giants would be impressive. Thousands of worlds of many kinds are more than impressive. They force us to imagine that planet formation is a normal act of the galaxy. Stars are not lonely points. They are often centers of systems. Around them, matter organizes into disks, rings, worlds, moons, belts, and debris. The galaxy is architectural, but architecture is not habitation. A house shape does not guarantee a home. A world shape does not guarantee life. Even Earth was not always comfortable. For much of its history, life was microscopic. Complex organisms came late. Technological civilization came almost impossibly late, measured against the planet's age. If Earth is our only example, then we must be careful. We do not know whether our path is typical, rare, or bizarre. This uncertainty cuts both ways. It could mean life is so natural that it appears whenever conditions allow. It could mean Earth passed through a chain of unlikely gates. It could mean simple life is common, but intelligence is a narrow accident. It could mean intelligence is common, but detectable technology is brief. It could mean we are early, late, isolated, surrounded, ignored, or simply not listening correctly. Every option changes the emotional meaning of deep space. If life is common, then the universe is more alive than it looks. If life is rare, then Earth is more fragile than we feel. If intelligence is common but silent, then communication may be the wrong expectation. If intelligence is rare, then our responsibility becomes larger. No confirmed result yet chooses among these possibilities. That is the ache of the present moment. We have enough evidence to ask the question scientifically, but not enough to answer it finally. We have moved beyond pure speculation, but not into certainty. We are suspended between ignorance and revelation, and every new telescope pulls the rope tighter. This is where the word worry finally becomes useful. Not fear, not dread, not panic. Worry as sustained attention. Worry as the refusal to look away from a difficult pattern. Worry as the emotional shadow of responsibility. Scientists are starting to worry about what we are finding in deep space, because the findings are not lining up into a simple worldview. They are not saying the universe is empty. They are not saying it is crowded. They are not saying life is common. They are not saying life is rare. They are not saying our models are useless. They are not saying our models are complete. They are saying, keep looking, but be prepared to change. That is a hard message for any civilization. Civilizations prefer certainty. They build myths, maps, institutions, and identities around the idea that the world is mostly understood. Science does the opposite at its best. It builds reliable knowledge while preserving the ability to be corrected. That makes it powerful, and also psychologically demanding. Deep space is now correcting us in several languages at once. In ancient infrared light, in planetary shadows, in atmospheric absorption, in radio silence, in cometary chemistry, in the motion of objects that do not belong to our star. We are learning to translate those languages. But translation is slow. Some words are missing. Some grammar is unfamiliar. Some signals are too faint to hear clearly. Some meanings change when more context arrives. Still, the message is becoming harder to ignore. The universe is not waiting at the edge of knowledge as a single secret to be unlocked. It is unfolding as a series of deeper corrections, and correction is rarely finished in one generation. A single generation of scientists may build the telescope, design the survey, process the first data, argue over the first strange objects, and leave the deeper answer to people who are not yet born. That is normal in astronomy. The universe is too large, too old, and too layered for one human lifetime to close every question it opens. This is part of why deep space discoveries feel different from discoveries on Earth. On Earth, an unknown species can be photographed, sampled, sequenced, and placed into a tree of life. A mineral can be cut, weighed, analysed, and compared in a laboratory. A weather pattern can be measured by instruments inside the atmosphere itself. But deep space gives us distance. It gives us delay. It gives us fragments of information separated from the systems that produced them. So astronomy often advances like archaeology carried out from another continent, using light instead of tools. A distant galaxy is not available to dig through. We cannot stand inside it and count its stars. We cannot watch its first stellar generations form in real time. We receive light, model it, compare it, and ask what history could have produced it. An exoplanet is not available to walk across. We cannot scoop its clouds or taste its oceans. We watch its star dim, measure tiny changes in colour, infer size, orbit, atmosphere, and temperature from signals that can be overwhelmed by noise. Even an interstellar object closer than galaxies and planets around other stars remains difficult. It moves quickly. It may be discovered late. It may already be fading. Its activity can change as sunlight warms it. Its surface may not reveal its interior. Its chemistry is accessible only through the gases and dust it releases, and even those must be interpreted through instruments, models, and time. This means deep space science is always partly an act of reconstruction, and reconstruction requires humility. Imagine finding a single burned page from a book written in another language, carried by wind across an ocean. You can study the ink, the fibres, the handwriting, and the surviving words. You can learn a great deal, but you cannot pretend you have the whole library. This is what many cosmic discoveries are like. A galaxy's spectrum is a page. A planet's transit is a page. A non-detection is a blank page with a date, instrument, and threshold written on it. An interstellar comet is a torn page from a different star's formation history. The mistake is to treat a page as the whole book. The miracle is that the page exists at all. That miracle is easy to miss when discoveries arrive quickly. We become used to headlines: another galaxy candidate, another exoplanet, another spectrum, another search, another comet, another constraint. But beneath each announcement is a chain of human and technical achievement: mirrors polished to extreme precision, detectors cooled to reduce noise, algorithms written to separate signal from artifact, teams checking calibrations, observers scheduling scarce telescope time, engineers maintaining instruments in environments no human hand can easily reach. Deep space discovery is not casual. It is built on patience, layered over machinery, layered over mathematics, layered over doubt. And doubt may be the most important layer. Without doubt, every exciting signal would become a false revelation. Without doubt, every early galaxy would be declared impossible before its uncertainties were understood. Without doubt, every planet in the habitable zone would be marketed as a second Earth. Without doubt, every strange interstellar object would become evidence for whatever story people already wanted to believe. Doubt slows the story down, but it protects the truth. This is why the real scientific reaction to deep space discoveries is often less dramatic than the public reaction, but more consequential. The public asks, what does it mean? Science first asks, is it real? Then, how certain is it? Then, what else could explain it? Then, can another instrument confirm it? Then, does it apply broadly or only to this object? Then, only after that, what does it mean? That order matters. Meaning is last because meaning is expensive. It must be paid for with evidence. And deep space makes evidence expensive in every sense. Expensive in money, because the instruments are enormous. Expensive in time, because observations are limited. Expensive in analysis, because faint signals require careful processing. Expensive in patience, because confirmation may take years. Expensive in humility, because the first interpretation may not survive. But when meaning finally emerges, it changes the foundation. The discovery of exoplanets changed the foundation. The sky stopped being only stars and became systems. The detection of cosmic background radiation changed the foundation. The early universe became observable as a thermal fossil. The confirmation of gravitational waves changed the foundation. Space-time stopped being only a mathematical stage and became something whose ripples could be measured. Images of black hole shadows changed the foundation. The most extreme predictions of gravity acquired a dark, visible outline. The current wave of deep space findings may be doing something similar, though more gradually. It may be changing the foundation from a universe of isolated wonders to a universe of connected processes. Early galaxies are not just distant objects. They are part of the story of how matter became chemically rich enough for later planets. Exoplanets are not just distant worlds. They are part of the story of how common planetary environments may be. Atmospheres are not just layers of gas. They are part of the story of whether chemistry can become detectable across distance. SETI. Silence is not just failure. It is part of the story of how hard intelligence may be to find. Interstellar objects are not just passing debris. They are part of the story of how planetary systems exchange material with the galaxy. Everything begins to connect. That connection is beautiful, but it is also unsettling because it means a change in one frontier can alter the meaning of another. If early galaxies formed stars and heavy elements faster than expected, then the chemical readiness of the universe may have advanced earlier in some places. If planets are extremely common, then the search for life becomes less about whether worlds exist and more about which worlds remain stable enough. If atmospheres are difficult to interpret, then life may be harder to prove than to imagine. If technosignature searches remain silent, then intelligence may require a different search strategy or a deeper understanding of time. If interstellar objects are common, then planetary systems may be more physically connected than we once assumed. The universe is not a set of separate mysteries. It is one system showing different faces. That is why the worry feels cumulative. It is not the worry of one anomaly. It is the worry that comes when several independent lines of evidence all say, "Your picture was too small. The picture of early time was too simple. The picture of planetary systems was too local. The picture of habitability was too hopeful. The picture of silence was too vague. The picture of the solar system as isolated was too sealed." Each correction is manageable by itself. Together, they form a psychological shift. And human beings do not always handle psychological shifts gracefully. We may respond by exaggerating, because exaggeration feels like control. We may respond by denying, because denial feels safer than uncertainty. We may respond by turning science into entertainment, stripping away the careful boundaries that make it reliable. Or we may respond by accepting the discomfort and learning to think with more precision. The last response is the hardest. It is also the only one worthy of the evidence, because deep space, if it teaches anything, teaches that scale punishes arrogance. The universe is not obligated to make our categories useful. It can produce planets between sizes we expected. It can form systems with architectures absent from our own. It can create early galaxies that sit near the edge of our models. It can allow life to be rare or common without regard for what would comfort us. It can remain silent without explaining why. And yet, it also allows us to learn. That is the paradox. We are small enough to be corrected, but capable enough to notice the correction. We are brief enough that ancient light dwarfs our entire species, but clever enough to build detectors that catch it. We are local enough to know only one living world, but ambitious enough to search for atmospheric chemistry on others. We are young enough as a technological civilization that our listening window is almost nothing, but aware enough to understand that this weakness matters. There is dignity in that awareness. Not cosmic importance, not centrality, but dignity. The dignity of a species trying not to lie to itself while looking into darkness. This may be the emotional heart of the entire story. The universe is not frightening because it is about to reveal a monster. It is frightening because it reveals how often we have mistaken a local viewpoint for a universal one. Earth felt like the ground of reality until astronomy moved it. The sun felt central until the galaxy moved it. The Milky Way felt like the universe until other galaxies moved it. Now our assumptions about planets, life, silence, and early cosmic history are being moved too. The correction continues, and maybe it will never fully stop. Future astronomers may look back at our era the way we look back at the first exoplanet detections. Revolutionary, but primitive. They may have catalogues of small rocky planets with measured atmospheres. They may know whether common red dwarf planets keep air. They may have intercepted or visited an interstellar object. They may have mapped the earliest galaxies with enough detail to make today's tensions seem like the first rough sketch. They may have found a biosignature, or ruled out many optimistic possibilities, or discovered that life is hiding in places our current methods cannot reach. They may know answers we cannot imagine, or they may inherit deeper versions of our questions. That is the nature of the frontier. It recedes as we approach, but not because progress is fake. It recedes because every answer reveals the next layer of structure. A child asks why the sky is dark. A scientist answers with cosmic expansion, stellar lifetimes, finite age, light travel time, and the distribution of galaxies. Then a deeper question appears. What shaped those galaxies? What drives expansion? What is dark energy? What happened before the first stars? Knowledge does not end mystery. It refines it. This is what is happening now with deep space. The mystery is being refined. It is becoming more technical, more precise, more constrained, and in some ways more profound. A vague alien fantasy is easy to imagine and easy to discard. A carefully measured atmosphere with ambiguous chemistry can occupy a field for years. A fake, impossible galaxy headline disappears quickly. A real tension in early star formation can reshape simulations. A dramatic claim about a signal may collapse under interference checks. A well-defined non-detection can guide the next search. The refined mystery lasts longer. It also asks more of us. It asks us to care about the difference between candidate and confirmed, between life and chemistry, between silence and absence, between anomaly and artifact, between model pressure and model failure, between alien as not from here and alien as alive or intelligent. These distinctions may sound small, but they are the difference between understanding the universe and using the universe as a screen for our fears. Deep space deserves better than projection. It deserves attention. And attention, when sustained long enough, becomes a kind of reverence. Not mystical reverence, but the reverence of refusing to simplify what is genuinely complex. A distant galaxy is allowed to be faint, ancient, uncertain, and important all at once. A planet is allowed to be promising, hostile, beautiful, and lifeless. A silent star system is allowed to deepen the question without answering it. An interstellar object is allowed to be natural and still astonishing. This kind of reverence is quieter than fear. It does not need urgent music. It does not need a false countdown. It does not need to tell us that scientists are hiding something or that everything we know is wrong. It only needs the truth. Our best instruments are beginning to show us a universe whose details are more surprising than our slogans. And perhaps that is enough. Perhaps it is more than enough. Because if the universe is more surprising than our slogans, then the honest path forward is not to invent louder slogans. It is to become better listeners, to build better instruments, to ask cleaner questions, to let uncertainty remain where it belongs, to let evidence accumulate without forcing it into a shape too soon. That is what scientists are doing when they worry. They are listening carefully to a universe that has started speaking in finer detail than before. And finer detail can be more unsettling than darkness. Darkness gives the imagination room to invent anything. Detail removes that freedom. It says, this molecule may be here, but not that one. This galaxy may be early, but its mass is uncertain. This planet may be rocky, but its atmosphere may be gone. This signal may be interesting, but it may also be interference. This visitor may come from another star, but its path and chemistry must be explained before its story can be told. Detail is where fantasy begins to lose authority. That is why the new deep space era feels so strange. We are not merely discovering that the universe is vast. That lesson is old. We are discovering that vastness has texture. The early universe had regions of activity. Planetary systems have architectures. Atmospheres have histories. Silence has limits. Interstellar objects have chemistry. The unknown is becoming less like a blank wall and more like a surface covered in faint writing. And faint writing is harder to ignore than a blank wall. A blank wall lets us say, maybe anything is true. Faint writing says, something specific is true here, but you do not yet know how to read it fully. That is the modern human position in deep space. We can read some of the writing, not all of it. Enough to know it matters. Not enough to stop arguing about what it means. This tension is especially powerful around the early universe. When astronomers look toward the most distant galaxies, they are not simply filling an album with old photographs. They are testing the growth of cosmic structure. In the standard broad picture, tiny density differences in the early universe grew under gravity. Dark matter helped create scaffolding. Gas fell into halos. Stars ignited. Galaxies assembled through accretion, mergers, feedback, and time. That picture is strong, but strength does not mean every detail is settled. The first galaxies lived in conditions we cannot recreate. Gas clouds were different. Metal content was lower. Radiation fields were harsh. Stellar populations may have been unlike those nearby today. Black hole seeds may have formed in ways still debated. The first cycles of star birth and death may have enriched their environments unevenly. The universe at those ages was not simply a smaller version of the present. It was a different physical regime. So when observations show early galaxies that look bright, compact, chemically suggestive, or surprisingly organized, the question is not whether the entire cosmic framework collapses. The question is whether the recipes inside that framework are complete. How efficiently did early gas become stars? How bursty was star formation? How much light came from young, massive stars? How much was hidden or altered by dust? How quickly did the first supernovae enrich surrounding gas? Could some galaxies be magnified by gravitational lensing? Are we overestimating stellar mass because the light is dominated by a small number of extremely bright young stars? Each answer changes the meaning of the observation, and each answer also changes the history that eventually leads to us. Because heavy elements are not decorative details, they are the material basis of planets like Earth. Oxygen, carbon, nitrogen, silicon, iron, these are not primordial gifts in abundance. They are products of stars and stellar death. The atoms in bodies, oceans, rocks and air came from processes that unfolded across cosmic time. When we study early enrichment, we are not only studying distant galaxies, we are studying how quickly the universe began making the ingredients that later made planets possible. That is why the early universe pressure connects so naturally to exoplanets. A galaxy becomes chemically richer later. Stars form from enriched gas. Around some of those stars, disks gather dust and ice. Dust becomes pebbles. Pebbles become planetesimals. Planetesimals collide into planets. Some planets keep atmospheres, some lose them. Some cool, some melt. Some become ocean worlds, desert worlds, mini Neptunes, lava planets, or frozen bodies under distant suns. The path from early light to later worlds is long, but it is continuous. Deep space is not separate stories. It is one history told at different distances. A telescope looking at a galaxy near the cosmic dawn and a telescope measuring an exoplanet atmosphere are studying different chapters of the same book. One asks when the universe began making complexity. The other asks what that complexity became around ordinary stars. The SETI telescope asks whether complexity ever became technology elsewhere. The survey that catches an interstellar object asks what debris those planetary systems have thrown into the dark between stars. This is why the findings feel cumulative. They are not identical, but they rhyme. Everywhere we look, the universe seems to be turning simple beginnings into complicated outcomes. Smooth early matter becomes cosmic web. Gas becomes stars. Stars make elements. Elements become dust. Dust becomes worlds. Worlds become environments. Environments may become life. Life may become mind. Mind may become technology. Technology may become detectable, or may disappear before anyone else can notice. The chain is majestic. It is also fragile. Break one link, and the later story changes. If early enrichment is rare, planets like ours appear later or less often. If rocky planets lose atmospheres around common star types, habitable worlds may be less common than planet counts suggest. If life is difficult to start, then chemistry alone is not enough. If intelligence is rare, then a living universe may still be quiet. If technology is brief, then civilizations may pass each other in time without ever overlapping. The title's worry lives inside that chain, not in one alien signal, not in one impossible object, in the fragility of the steps between matter and meaning. For all our discoveries, we still do not know how many of those steps are ordinary. We know planets exist in abundance, but not how often they become stable homes. We know chemistry is widespread, but not how often chemistry becomes biology. We know intelligence can evolve once, but not whether it is a repeated outcome or a rare accident. We know technology can produce signals, but not how long such signals remain visible across space. We know interstellar objects travel between systems, but not how representative the ones we have seen truly are. Each unknown sits inside a larger known. That is what makes it powerful. We are not in total darkness. We are in partial light. And partial light can be more disturbing because it reveals the shape of the unanswered question. Imagine a dark room. In total darkness, you can imagine the room is empty. But when a narrow beam of light crosses the floor and reveals footprints, dust, tools, and half-built structures, the room becomes more mysterious, not less. You know something is there, you just do not yet know the whole arrangement. Modern astronomy has turned on that narrow beam, and the floor is not empty. There were early galaxies where we expected fewer bright structures. There are planets around stars in almost every direction we learn to search. There are atmospheric signals that tempt us and then demand restraint. There are radio observations that make silence more exact. There are interstellar bodies moving through our system with histories that began elsewhere. None of this tells us the final answer, but it tells us the old emptiness was never real. That may be one of the deepest emotional corrections. Deep space looked empty because our senses are poor instruments. Human eyes see a handful of stars under good conditions. Human lifetimes cannot watch galaxies evolve. Human bodies cannot feel radio waves from distant pulsars or infrared light from the first galaxies. We evolve for forests, coasts, storms, predators, seasons, and faces. The universe we are now measuring was never available to our instincts, so our instincts are constantly behind. They tell us a galaxy is just a smudge. The data say it may be a city of stars seen near the beginning of time. They tell us a planet is just a dot we cannot see. The data say its atmosphere may hold chemical clues. They tell us silence means nothing. The data say silence, under measured conditions, is a result. They tell us a comet is a wandering ice ball. The data say this one may not have formed around the sun. Science is the process of replacing instinct with tested perception. And tested perception is often less comforting. It shows us that what looks small may be enormous. What looks empty may be crowded. What looks promising may be hostile. What looks silent may only be beyond our listening. What looks strange may be natural. What looks natural may still be unlike anything in our local experience. The emotional challenge is learning to feel awe without needing certainty. This is difficult because certainty is emotionally efficient. It closes the loop. It says aliens exist or they do not. Life is common or it is not. The Big Bang is broken or it is secure. Earth is special or it is ordinary. But the actual evidence resists those clean endings. It asks us to stay open while becoming more precise. That is a rare mental state. Open, but not gullible. Precise, but not closed. Curious, but not reckless. Skeptical, but not numb. The best response to deep space requires all four. It requires openness because the universe has repeatedly surprised us. It requires precision because surprise does not equal proof. It requires curiosity because there are still enormous questions worth asking. It requires skepticism because the most exciting claims are often the easiest to exaggerate. When scientists worry, they are often holding those four states at once. They are worried that a claim may outrun evidence, worried that a model may be missing something important, worried that public language may turn uncertainty into misinformation, worried that instruments may be biased in ways not yet fully understood, worried that an exciting clue might vanish under better data, worried, too, that a clue might not vanish and that if it stays, the field will have to change. That last kind of worry is the most productive. It is the worry that keeps a scientist awake, not because the discovery is frightening, but because it may be real. Real enough to demand follow-up, real enough to expose weakness in a model, real enough to show that a familiar category was too narrow, real enough to become part of the next generation's textbook. This is the kind of worry that built modern astronomy in the first place. The orbit of Mercury did not fit perfectly. The expanding universe did not fit old assumptions. The cosmic microwave background was not expected by everyone. Pulsars were strange. Quasars were strange. Exoplanets were once uncertain. Dark matter and dark energy remain deeply strange, not because they are fantasies, but because something measurable is missing from the simple picture. Deep space has always worried science into becoming larger. The difference now is that the worrying evidence is arriving from many frontiers at once. Early time, distant worlds, possible biosignatures, technosignature silence, interstellar debris. Each frontier presses a different part of the same human illusion, that our current map is close to complete. It is not, but that is not a failure. It is an invitation to keep drawing, and the map we keep drawing is no longer flat. It has depth now. Time depth, chemistry depth, silence depth, instrument depth. A galaxy is not just placed on the sky, but on a timeline. A planet is not just counted, but placed inside an architecture. A spectrum is not just a coloured line, but a record of atoms and molecules interacting with light. A non-detection is not just absence, but a measured boundary. An interstellar object is not just a moving point, but a fragment with a birthplace somewhere beyond the sun. This is what makes the new map so difficult to hold in the mind. It does not fit into a single image. A familiar map shows land, water, borders, roads, and names. A cosmic map must show where and when. It must show how far light travelled, how much space expanded, what wavelength shifted, what instrument could see it, what physical process made it visible, and what uncertainty remains. The result is not a simple picture of space. It is a layered reconstruction of reality from signals that have crossed enormous distances, and every layer adds room for surprise. The early universe layer says, the first luminous systems may have formed in bursts, clusters, and environments more intense than our simple mental dawn. The exoplanet layer says, planetary systems do not politely imitate the solar system. The atmosphere layer says, gases are clues, but clues are not verdicts. The technosignature layer says, if anyone is out there, Finding them is not as simple as pointing a radio dish and waiting for hello. The interstellar object layer says, other systems can lose pieces, and some of those pieces can pass through ours. Put together, the layers create a universe that feels less empty, but not necessarily friendlier. That is an important distinction. A crowded universe is not automatically a comforting universe. It may be crowded with dead worlds. It may be crowded with chemistry that never becomes life. It may be crowded with microbial biospheres buried where telescopes cannot detect them. It may be crowded with civilizations separated by time, using technologies invisible to us, or lasting too briefly to overlap. It may be crowded with early galaxies, planets, debris, radiation, and hidden processes, while still leaving consciousness rare. Or it may not. The honest answer remains open, but the old emptiness is gone. We know too much for that. We know planets are common. We know galaxies filled the universe long before the sun existed. We know organic chemistry is not confined to Earth. We know comets, asteroids, disks, and clouds carry carbon-bearing molecules. We know interstellar space is not a perfect void. We know silence, when searched carefully, can be defined in ways that matter. We know the cosmic story has many more active parts than the night sky suggests to the unaided eye. So the worry shifts. It is not, what if space is empty? It is, what if space is full of almost answers? Almost life, almost Earths, almost signals, almost early model-breaking galaxies, almost interpretable atmospheres, almost reachable interstellar samples, almost enough evidence to change everything, but not enough yet to say so cleanly. Almost answers are exhausting. They are also the frontier. A confirmed answer gives closure. An almost answer gives work. It asks for another observation, another model, another telescope, another year, another team. It refuses both denial and certainty. It keeps the question alive in the most productive and uncomfortable way. That is where deep space science lives now. Not in ignorance, and not in final revelation. In the pressure of almost. An early galaxy almost fits, but not comfortably. A planet almost resembles Earth, but with missing context. An atmosphere almost suggests something interesting, but not enough to remove non-biological explanations. A radio search almost says something about cosmic company, but only within the narrow boundaries it actually tested. An interstellar object almost lets us sample another system, but not enough to reconstruct its entire origin. This almost state is not failure. It is the normal shape of knowledge before the next leap. When astronomers argue over early galaxies, they are not merely disagreeing, they are sharpening the measurement until the false parts fall away. When exoplanet scientists debate atmospheres, they are not weakening the search for life, they are making sure that a future claim will be worthy of belief. When SETI researchers publish non-detections, they are not admitting defeat, they are building a map of where certain kinds of signals are not. When interstellar object researchers compare chemistry, they are not making the visitor less strange by explaining it naturally. They are turning strangeness into information. Information is more durable than excitement. Excitement fades if it has nothing beneath it. Information can be revisited, combined, corrected, and used. A careful measurement becomes part of a future pattern. A limit becomes part of a future search. A disputed interpretation becomes a better model. A strange object becomes a class. A class becomes a population. A population becomes a new understanding of how common something really is. This is why the first examples matter so much. The first exoplanets changed the question from, do planets exist elsewhere? To, how many kinds are there? The first confirmed interstellar object changed the question from, can objects from other systems pass through ours? To, how often, and what are they made of? The first strong looks at very early galaxies changed the question from, can we see the cosmic dawn? To, what was happening there, and how fast? Every first detection is a doorway. The worry comes from seeing how many doorways have opened at once. Behind one door is the early universe, not as a smooth, abstract beginning, but as a place of early structure, radiation, collapse, and chemical birth. Behind another is the population of planets, not as rare gems, but as countless outcomes of disk physics and gravitational chaos. Behind another is the life question, stripped of fantasy and made chemically difficult. Behind another is the intelligence question, stripped of romance and made observationally brutal. Behind another is the galaxy as a traffic field of debris, with fragments travelling between stars. And behind all of them is the same realization. The universe has more history than our categories. Our categories are tools, not truths. Galaxy is a category, but a young galaxy at extreme redshift, a quiet spiral, a violent merger, a dwarf satellite, and a massive dusty starburst are not the same story. Planet is a category, but a hot Jupiter, a super-Earth, a mini-Neptune, a tidally locked rocky world, a rogue planet, and Earth are not the same story. Signal is a category, but a natural pulse, human interference, a narrowband candidate, and a confirmed technosignature would not be the same story. The universe hides complexity inside simple nouns. Better science opens the nouns. That is why saying, "we found a planet," no longer feels like the end of a sentence. What kind of planet? Around what kind of star? With what radius, mass, orbit, density, atmosphere, temperature, and history? Saying, "we found an early galaxy," now opens another chain. How early? How bright? How certain is the redshift? What does the spectrum show? How much stellar mass is inferred? Could dust or lensing affect the interpretation? Does it represent a population or an outlier? Every answer becomes a doorway to a more precise question. This can make the public feel as if science never settles anything. But that is not true. Science settles many things. It settled that Earth orbits the Sun. It settled that stars are other suns. It settled that the Milky Way is not the entire universe. It settled that the universe is expanding. It settled that planets exist around other stars. It settled that black holes are real astrophysical objects. It settled that gravitational waves can be detected. It settled that interstellar objects exist. What remains open is not a sign that science is weak. It is a sign that science has reached the living edge. At the living edge, knowledge is strong behind us and flexible ahead of us. Behind us are foundations. Ahead are revisions. The danger comes when people confuse the flexibility ahead with weakness behind. A debate over early galaxy formation does not erase cosmic expansion. A debate over a possible biosignature does not erase exoplanet science. A non-detection in SETI does not erase the value of searching. A natural explanation for an interstellar object does not erase its importance. The frontier is allowed to be uncertain. That is what makes it a frontier. And perhaps the deepest discomfort is that humanity is no longer outside that frontier as a passive observer. Our technology is now good enough to participate in the sorting. We are not merely telling stories under the stars. We are building instruments whose results can force the stories to change. That gives us power, but also exposes our immaturity. We want the answers faster than the evidence can safely deliver them. Deep space will not move at the speed of our attention span. The universe has already taken billions of years to prepare the light and matter we are now measuring. It does not owe us a simple conclusion this year, or this decade. Some questions may require instruments not yet launched. Some may require statistical populations not yet collected. Some may require theories not yet written. Some may require a discovery that happens tomorrow by chance, or a century from now through patience. Still, the direction is clear. The darkness is becoming legible. Not fully, not comfortably, but enough to change the way we ask. That is the title's real transformation. Scientists are not starting to worry because deep space has become threatening. They are starting to worry because deep space has become legible enough to challenge shallow certainty. It is no longer a place where vague awe can hide from measurement. It is a place where awe must stand beside data. And when awe stands beside data, it becomes heavier. Awe without data floats. Awe with data has gravity. It pulls on our models, our language, our humility, our sense of Earth, and our expectations of life. It asks not just that we feel small, but that we think more carefully. The universe is not asking us to be afraid. It is asking us to grow up. And growing up, on a cosmic scale, means surrendering the need for every answer to feel simple. A simple universe would be easier to narrate. First, galaxies form slowly. Planets like Earth are common wherever conditions are pleasant. Life appears when water appears. Intelligence announces itself across the stars. Strange objects are either ordinary or extraordinary, with nothing difficult in between. Silence means loneliness. Chemistry means life. Distance means emptiness. But the universe we are finding is not that clean. It is full of intermediate states. Galaxies that are not impossible, but earlier than expected. Planets that are not Earth's, but not irrelevant either. Atmospheres that are not proof of life, but not meaningless. Silent searches that do not prove absence, but still erase some easy possibilities. Interstellar objects that are natural, but still foreign in origin. Every category has a middle, and the middle is where the science becomes real. That middle is hard for public imagination because it lacks the satisfaction of extremes. It does not give us the thrill of confirmed alien contact or the comfort of confirmed cosmic emptiness. It does not let us declare that physics has collapsed or that every model was already right. It says something more demanding. The universe is behaving within law, but not within our simplified expectations. That is the kind of correction that lasts. A miracle can be dismissed by people who do not believe in miracles. A threat can be sensationalized and then forgotten. But a careful pressure on models, repeated across different frontiers, changes the intellectual landscape. It forces new simulations, new telescope proposals, new observing strategies, new definitions, new caution in language, and new patience in the public conversation. This is what deep space findings are doing now. They are teaching science to move away from the fantasy of one decisive clue. The universe may not answer with one clue. It may answer with accumulation, a population of early galaxies, a catalogue of planet types, repeated atmosphere measurements, years of non-detections, a growing sample of interstellar visitors, better statistics, better errors, better constraints. The answer may not arrive as a lightning strike. It may arrive as a shape slowly emerging from fog. And the shape may be stranger than any single headline. For example, the future may show that early galaxies were not violating cosmology, but that star formation in the first few 100 million years was more bursty, efficient, and environment-dependent than older models captured. That would not be a collapse of science. It would be science becoming sharper. The future may show that planets are common almost everywhere, but long-term surface habitability is much rarer than raw planet counts imply. That would not make exoplanet discoveries less important. It would make them more serious, because the difference between a planet and a home would become clearer. The future may show that life leaves atmospheric clues only under certain conditions, or that many biospheres are hidden beneath ice or oceans, or that some non-biological chemistry imitates life better than we expected. That would not end astrobiology. It would force it to become more mature. The future may show that technological civilizations are hard to detect, not because they are absent, but because detectable phases are brief, signals are narrow, methods differ, or timing rarely overlaps. Or it may show that intelligence is truly rare. Either result would reshape the human story. The future may show that interstellar objects are common messengers of planetary formation, passing constantly through the solar system unseen, carrying chemical diversity from stars we will never visit. That would make our system feel less isolated, not because it is crowded with intention, but because it is part of a galaxy where matter has always been moving. None of these possibilities is cheap. Each one would require work. Each one would refine the meaning of what we have already found. Each one would make the title's worry more precise. Not fear of danger, but fear of misunderstanding. Misunderstanding is the enemy here. Misunderstanding turns an early galaxy into a fake claim that the Big Bang is dead. It turns an atmospheric molecule into premature life detection. It turns a radio non-detection into proof that no one exists. It turns a natural interstellar comet into an artificial probe. It turns scientific caution into conspiracy, and scientific revision into weakness. But revision is not weakness. Revision is the strength that lets science survive contact with reality. A belief system that cannot revise must defend itself from evidence. Science, at its best, does the opposite. It invites evidence to hurt it. It builds instruments powerful enough to expose its own incomplete parts. It sends telescopes into space, knowing they may return with data that make old explanations uncomfortable. It listens to the sky, knowing silence may be harder to interpret than a signal. It names uncertainty instead of hiding it. That is a rare human achievement, and deep space rewards it with a kind of honesty that can feel cold, but is actually generous. The universe gives us no flattery. It does not place Earth at the centre. It does not guarantee company. It does not arrange planets to match our hopes. It does not make early galaxies easy for our models. It does not turn every strange object into a message, but it does give us traces, light, shadows, spectra, orbits, absences, chemical signatures, fossil radiation, moving points against the background stars. Enough to learn, not enough to become arrogant. That balance may be exactly what we need. A civilization with too little knowledge lives inside myth. A civilization with too much false certainty lives inside arrogance. A civilization that can measure its own uncertainty has a chance to become wise. Deep space is pushing us toward that third state. It is asking us to hold real knowledge and real uncertainty together. To say, yes, galaxies formed early, but we are still learning how. Yes, planets are common, but homes may not be. Yes, chemistry can be measured, but life has not been confirmed. Yes, silence matters, but silence has many interpretations. Yes, other star systems can send objects through ours, but natural does not mean uninteresting. That way of thinking is slower. It is also more honest, and in the long run, honesty is more astonishing than exaggeration. Exaggeration burns brightly for a moment, then leaves distrust behind. Honesty accumulates. It lets a viewer return years later and find that the story still holds, even as details improve. It allows wonder to survive correction, because the wonder was never built on a lie. This is why the safest version of the title is also the strongest. Scientists are not starting to worry because deep space has revealed a monster. They are starting to worry because deep space has revealed discipline, the discipline of ancient light arriving with measurable structure. The discipline of planets obeying formation physics in forms we did not expect. The discipline of chemistry refusing to become proof before its time. The discipline of silence becoming a bounded result. The discipline of interstellar debris following natural trajectories across a porous solar system. The universe is not chaotic in the way fear wants it to be. It is orderly enough to study and varied enough to unsettle us. That combination is far more powerful. A lawless universe would teach us nothing. A perfectly simple universe would teach us once and then grow dull. But a lawful, varied, ancient, unfinished universe can keep teaching forever. It can show us that our models are useful but incomplete, that our categories are necessary but temporary, that our instruments are magnificent but young, and that our existence is both ordinary matter and extraordinary circumstance. There is humility in realizing that the atoms in our bodies were made by stars, but there is deeper humility in realizing we still do not fully understand how quickly the first generations of stars enriched the universe. There is wonder in knowing Earth is a planet among many, but deeper wonder in realizing that among many does not answer whether life is common. There is awe in listening for other minds, but deeper awe in admitting that silence may be a measurement of our limits, not a verdict on the galaxy. This deeper awe is quieter. It does not need to shout. It sits with the data. It allows a distant red smudge to remain a distant red smudge, while still recognizing that the smudge may have formed when the universe was young enough to challenge our sense of time. It allows a planet's atmosphere to be only a thin signal in starlight, while still recognizing that such a signal may someday change biology forever. It allows an interstellar object to be only ice and dust, while still recognizing that it formed under another sun. The truth does not become smaller when we remove the false drama. It becomes sharper, and sharp truth is what the next stage of astronomy will demand. As more powerful observatories come online, the public will face more almost answers, more disputed clues, more careful limits, more tempting phrases, more reasons to confuse excitement with confirmation. The responsibility will not belong only to scientists. It will belong to anyone who tells the story. The story must be allowed to breathe. It must say that some early galaxy findings may change with better data. It must say that a biosignature candidate is not life. It must say that silence is not proof of absence. It must say that interstellar origin does not imply intelligence. It must also say that none of those cautions makes the discoveries boring, because they are not boring. They are the most important kind of strange, the kind that survives careful speech. And perhaps that is the final lesson before the story begins to turn toward its ending. The universe we are finding in deep space is not less mysterious because science is cautious. It is more mysterious because caution reveals how much remains after exaggeration is removed. Take away the alien myth, and an interstellar object is still a fragment from another star. Take away the "Big Bang is broken" headline, and an early galaxy is still a challenge to formation history. Take away the second Earth language, and a rocky exoplanet is still a world with a story. Take away the "we are alone" conclusion, and a silent search is still a boundary around possibility. Take away the hype, and deep space is still overwhelming. That is how we know the mystery is real. Real mystery does not depend on distortion. It remains after distortion is gone. It remains in the redshift, in the transit curve, in the spectrum, in the non-detection, in the orbit, in the cold mathematics of light moving across time. It remains because the universe itself is not simple enough to be exhausted by our first explanations. So the worry continues. Not as fear, as attention, as a careful hand hovering over a new image, knowing that the faint thing on the screen may not be what anyone hoped, may not be what anyone feared, but may still be important enough to change the next map. And the next map will not be drawn by one telescope alone. It will be drawn by overlapping instruments, each seeing a different kind of truth. Infrared observatories will keep reaching toward the earliest galaxies, where ancient light has been stretched beyond visible colours. Radio telescopes will keep listening through static, interference, and cosmic background noise. Planet surveys will keep watching stars dim by tiny fractions as worlds cross their faces. Spectrographs will keep pulling chemical fingerprints from starlight. All sky surveys will keep scanning for fast-moving objects before they vanish into distance again. The future of deep space discovery is not a single eye. It is a network of different ways to notice. That matters because no one instrument sees the whole universe. A telescope sensitive to infrared light can reveal cold dust, distant galaxies, and atmospheres in ways optical telescopes cannot. A radio dish can detect emissions invisible to the eye. A transit survey can find planets by shadows, but misses systems whose orbits are not aligned from our perspective. Direct imaging may reveal wide, young, giant planets, but not the small, close-in worlds that transit surveys favour. Every method has power, and every method has blindness. So the universe we know is always shaped by how we look. This should make us humble, because the next method may change the sample. The next survey may reveal that objects we thought were rare were only difficult to detect. The next detector may show that a pattern was biased. The next telescope may turn an almost answer into either a false alarm or a foundation. This has happened before, and it will happen again. Before exoplanet searches matured, The solar system seemed like the natural planetary template. Then we found hot Jupiters, then super-Earths, then mini-Neptunes, then compact multi-planet systems, then planets around stars unlike the Sun. Each detection method opened a different piece of the architecture. The universe did not change, our sample did, and when the sample changed, the theory had to follow. The same may be true for the early universe. Today's most distant galaxies may look surprising because we are seeing the brightest tip of a hidden population, or because early star formation was more efficient, or because some objects are affected by lensing, or because our assumptions about stellar populations, dust, or black holes need refinement. The only way forward is not to pick the most dramatic interpretation, but to increase the sample, improve the spectra, compare independent observations, and test the models until the pattern becomes harder to avoid. If the pattern weakens, that is knowledge. If the pattern strengthens, that is knowledge too. Science wins either way, as long as the process is honest. This is where the public often misunderstands scientific uncertainty. When scientists revise an early claim, it can look like failure. But revision is often the sign that the machinery is working. A galaxy candidate may move to a different redshift. A mass estimate may shrink. A possible molecule may vanish under new analysis. A strange signal may become interference. None of that means the search was pointless. It means the difference between reality and first impression was taken seriously. The universe deserves that seriousness. It is too easy to turn deep space into a mirror, to see our hopes in the planets, our fears in the silence, our fantasies in the interstellar objects, our impatience in the early galaxies. But the scientific task is to do the opposite, to remove ourselves from the center of the interpretation, to ask what the light, motion, chemistry, and absence actually allow. That removal is hard. It is also liberating, because once we stop demanding that deep space confirm a human story, it becomes more interesting. A planet does not have to be a second Earth to matter. It can matter because it reveals a new pathway of planetary evolution. A silent search does not have to mean loneliness. It can matter because it narrows the range of detectable technology. An interstellar object does not have to be artificial. It can matter because it carries material from outside the solar system. An early galaxy does not have to break cosmology. It can matter because it teaches us how fast structure emerged. The most mature form of awe is not the one that asks the universe to perform for us. It is the one that allows the universe to be itself. And what it appears to be is astonishing enough. A universe where hydrogen clouds became stars, where stars made heavier elements, where those elements gathered into dust and rock, where planetary systems formed in thousands of variations, where some worlds may hold oceans, others molten surfaces, others thick envelopes of gas, others no atmosphere at all, where distant galaxies preserve the memory of early structure, where radio telescopes can search nearby systems for signals and return with meaningful silence, where fragments from other stars can pass through the solar system like cold evidence from another history. This is not a simple universe. It is a universe with memory. That memory is stored in light, in chemistry, in orbits, in temperature, in motion, in dust, in the absence of signals where we looked carefully and found none. Deep space is not only a place, it is a record. The further we look, the older some pages become. The closer we examine planets, the more local histories appear. The more we listen, the more silence becomes structured. The more we track interstellar objects, the more the solar system becomes part of a larger exchange. And the record is incomplete. That incompleteness is not a flaw in the story. It is the story. If the record were complete, there would be no frontier. But the frontier is exactly where the most human part of science lives. The ability to move through uncertainty without surrendering to fantasy. To be changed by evidence without demanding finality. To say, this is what we know, and then, with equal honesty, this is what we do not know yet. Those two sentences belong together. One without the other becomes dangerous. Knowledge without uncertainty becomes arrogance. Uncertainty without knowledge becomes confusion. Deep space science is forcing us to practice both at once. We know that early galaxies existed. We do not yet know every route by which the first luminous systems grew. We know that planets are common. We do not yet know how common living worlds are. We know that some atmospheres can be studied. We do not yet know how easily life can be recognized remotely. We know that careful searches have found no confirmed technosignature. We do not yet know what that silence means. We know that interstellar objects pass through the solar system. We do not yet know how many, how diverse, or what they reveal about planetary systems across the galaxy. These paired truths are stronger than simple claims. They can survive new data because they leave room for new data. That is what the best science communication must do. It should not pretend the mystery is solved. It should not inflate the mystery into deception. It should give viewers enough structure to feel the importance of the question, and enough caution to recognize where the answer has not yet arrived. This is difficult, but deep space rewards difficulty. The easy version of the title would say, scientists are frightened because they found something dangerous. The better version says, scientists are concerned because the universe is becoming measurable in ways that expose gaps in our understanding. The first version produces a quick reaction. The second produces a lasting thought, and lasting thought is rarer than reaction. A reaction ends when the headline fades. A lasting thought changes how someone looks at the sky afterward. It makes a star feel less like a decoration and more like a possible system. It makes silence feel less empty and more like a question with boundaries. It makes a red smudge in a telescope image feel like a time capsule. It makes a comet from beyond the sun feel like a reminder that the galaxy is not divided into sealed rooms. This is the quiet power of deep space discovery. It changes the meaning of ordinary darkness. A night sky can still look calm. The stars can still appear fixed. The darkness between them can still look empty. But after enough evidence, the mind no longer believes the appearance completely. It knows that the calm hides motion, formation, radiation, chemistry, collapse, planets, debris, and time. It knows that the darkness is not a lack of story, it is a limit of perception. And perception is changing. That may be the most important sentence in this entire journey. Perception is changing. Not the universe, not the laws, not the ancient light already on its way. What is changing is our ability to receive it, sort it, and understand what part of the darkness was never empty at all. We are entering an era in which more of the universe will become visible to instruments before it becomes emotionally manageable to us. That mismatch will create more worry. Some of it will be scientific worry, how to explain the data. Some will be public worry, how to interpret it without exaggeration. Some will be philosophical worry, what it means for Earth, life, intelligence, and our place in time. All three are real. All three deserve care. Because the findings in deep space are not just changing astronomy, they are changing the scale of self-understanding. A species that thought in landscapes learned to think in planets. A species that thought in planets learned to think in solar systems. A species that thought in solar systems learned to think in galaxies. Now we are being asked to think in galaxy populations, exoplanet statistics, atmospheric retrievals, technosignature limits, and interstellar traffic. The mental scale keeps expanding, and each expansion leaves old certainty behind. There is grief in that, but there is also freedom. The grief is losing simple stories. The freedom is gaining truer ones. And the truer story, so far, is not that deep space is hostile or friendly. It is that deep space is richer than our first stories allowed. It is ancient, active, chemically inventive, dynamically open, and only partly legible. It does not answer our questions in the order we ask them. It does not protect our assumptions. It does not hurry. It does not explain itself except through evidence. So we keep building ways to receive that evidence. Mirrors, dishes, detectors, algorithms, surveys, models, missions. Each one is a small human answer to a vast, non-human reality. Each one says, "We are not finished looking," and we are not finished looking because the act of looking has already changed us. At the beginning of this journey, the title sounded almost like a warning. Scientists are starting to worry about what we are finding in deep space. It could have meant danger. It could have meant hidden aliens, broken laws of physics, or something moving toward us from the dark. But the deeper version is quieter and more unsettling. Scientists are worried because the universe is becoming clearer. Clearer does not mean simpler. Clearer means the old blur is resolving into details we now have to explain. Early galaxies are not just distant smears. They are tests of how fast matter became organized. Exoplanets are not just entries in a catalogue. They are evidence that planetary systems are common, diverse, and often unlike ours. Atmospheres are not just thin layers of gas. They are hard-to-read chemical histories. SETI silence is not just emptiness. It is a measured boundary around certain kinds of signals. Interstellar visitors are not just curiosities. They are fragments from beyond the sun, crossing into our local sky. The worry is not that one discovery has answered everything. The worry is that many discoveries are making easy answers harder to keep. Deep space has not told us that we are alone. It has not told us that we are surrounded. It has not told us that life is common. It has not told us that life is rare. It has not told us that our models are useless. It has not told us that our models are complete. It has done something more difficult. It has shown us where our confidence thins. That thinning can feel uncomfortable because humans prefer edges. We prefer yes or no, empty or full, safe or dangerous, ordinary or impossible. But the universe keeps giving us in-between states. A galaxy that strains a model without breaking cosmology. A planet that is rocky without being Earth. A molecule that is interesting without proving life. A silence that matters without proving absence. A visitor from another star that is natural without being familiar. The in-between is where humility lives, and humility may be the true outcome of deep space science. Not humiliation, not despair. Humility. The recognition that our knowledge is real, but partial. Our instruments are powerful, but young. Our models are impressive, but revisable. Our world is precious, but not central. Our questions are ancient, but only now becoming measurable. This is a more mature form of cosmic awe. It does not need to pretend that every anomaly is a revolution. It does not need to force every planet into the shape of home. It does not need to turn silence into loneliness or chemistry into biology. It can let the evidence be exactly what it is, and still feel the weight of it, because the evidence is heavy enough. A photon from a galaxy near the beginning of time is heavy with history. It carries information from an era before Earth, before the Sun, before any familiar landscape existed. A planet passing in front of its star is heavy with possibility, even if that possibility later turns out to be hostile, airless, or strange. A radio non-detection is heavy with restraint, because it tells us what one careful search did not find. An interstellar comet is heavy with foreignness, not because it is intelligent, but because its ice and dust began somewhere else. These are not small things. They only seem small because they arrive as faint signals. That may be the final paradox of astronomy. The greatest changes in our worldview often arrive quietly. A dimming star, a spectral line, a red-shifted smudge, a wobble, a moving dot, a background glow, a silence where a signal might have been. The universe rarely explains itself in dramatic human language. It gives us traces, and asks whether we are patient enough to read them. Patience is the opposite of panic. So when we say scientists are worried, we should imagine not terror, but careful attention. A researcher checking whether a line in a spectrum is real. A team debating whether an early galaxy's brightness is telling us about mass, dust, lensing, or star formation. An observer returning to the same planet during another transit. A radio astronomer removing interference before deciding whether a signal deserves another look. A survey scientist calculating the orbit of a faint object and realizing it does not belong to the Sun. This is worry as responsibility. It is the responsibility not to overclaim, not to miss what matters, not to let old models become dogma, not to let public excitement turn uncertainty into misinformation, not to let caution drain wonder from the truth. That balance is difficult, but it is where the best science lives. And it is where this story ends. Not with a final answer, because there is none yet. Not with aliens, because none have been confirmed. Not with broken physics, because the evidence does not justify that. Not with cosmic danger, because the deep space findings we have followed are not threats moving toward Earth. The story ends with a quieter realization. Deep space is no longer distant in the old emotional sense. It is entering our measurements. It is pressing against our models. It is delivering light, silence, chemistry, and matter into the human record. The universe is becoming part of our evidence, and evidence changes a civilization more deeply than fear does. Fear fades when the imagined monster does not arrive. Evidence remains. It gets archived, reanalyzed, challenged, improved, combined with future observations. A faint galaxy today becomes a point in tomorrow's population study. A non-detection today becomes a limit in tomorrow's search strategy. A strange comet today becomes one example in a future census of interstellar objects. A debated atmosphere today becomes a lesson in how careful the life search must be. Nothing is wasted if it is measured honestly. Even uncertainty becomes useful. That is the lesson deep space keeps teaching. The unknown is not a wall. It is a landscape with fog over it. Each instrument clears a little more. Sometimes what appears is what we hoped. Sometimes what appears is stranger. Sometimes what appears removes a possibility we loved. Sometimes it opens one we had not imagined. But the clearing itself matters. We are watching the fog thin, and beyond it is not a simple answer. Beyond it is a universe with more texture than our first stories could hold. A universe where the early dawn may have been busier than expected. Where stars built elements that later built worlds. Where worlds formed in arrangements our solar system never showed us. Where habitability is delicate, chemistry is ambiguous, silence is structured, and even the space between stars is not entirely empty of travelers. A universe that does not center us, but does allow us to understand pieces of it. That allowance is extraordinary. There is no law that says conscious beings must be able to read ancient light. No law that says the universe must be transparent enough for galaxies to reveal their youth. No law that says planets around other stars must betray themselves by shadows and wobbles. No law that says interstellar fragments must occasionally pass close enough for us to notice. These are not promises made to us. They are opportunities we happen to become capable of using. For a brief moment in cosmic history, matter on one small planet has learned to study matter everywhere else. That is not centrality. It is participation. And participation comes with a new kind of responsibility. To tell the truth as carefully as we can. To let mystery remain mystery when it has not become discovery. To let discovery remain discovery when it has survived the tests. To keep wonder clean enough that it does not become deception. The title began with worry. It ends with vigilance. Scientists are starting to worry about what we are finding in deep space, because the findings are real enough to matter, strange enough to challenge, and incomplete enough to demand patience. The worry is a sign that the evidence has reached the edge of our old comfort. That is not a failure of science. It is the sound of science doing what it was built to do. A faint photon crosses billions of years. A telescope catches it. A detector records it. A human being asks what it means. And somewhere between the ancient light and the question, the universe becomes a little less silent, and humanity becomes a little less certain than before.